So perhaps we can start. So welcome to everybody to the last day of this workshop. Today we will four talks, and at the end the closing and prize. And the first talk of today is the one of Lorena Bocciu. It's my pleasure to introduce Lorena. Lorena is a professor at the North Carolina State University. She got her PhD under the supervision of Irena Daciaska. She was a principal investigator of several research projects. She is an expert on analysis and control of partial differential equations with application, for example, in linear wave equation and the fluid structure interactions. She is author of more than 40 papers and has about 500 citations. So please, Lorena, thank you again to accept our invitation.
Thank you, Jenny. Thank you for the nice introduction, and I want to thank all the organizers for putting together such a great conference. And thank you for inviting me. It is my pleasure to be here. So today I want to speak about multi-scale interface couplings of PDEs and ODEs, specifically with applications in tissue perfusion. So let me start by describing the model, right? And also why we got interested in this. So complex problems in science, engineering, and medicine often require the use of models that combine both systems of PDEs and ODEs. And these are known as multi-scale interface couplings. So what's the idea? The idea is the following. We have a local region of interest for which we provide, detailed, accurate, three-dimensional description. But at the same time, we want to account for the global features of the problem, right? And how do we do that? By using this so-called reduced lumped circuits, okay? So they're 0D models because they're ODs, they're just functions of time, right? So there's no space, so we call them 0D models. This is known as the multi-scale strategy, and it has been successfully used, especially for physiological flows. Like example, when you have blood flows in arteries or airflow in the bronchial tree. So in this case, they use either Stokes or Navier-Stokes equations to model a specific artery or a specific part of an artery. For example, let's say when you have a stent, right, in an artery, so you just model this area, the stented part of the artery, but then you use a systemic zero-dimensional lumped circuit model to approximate the remainder of the circulation. And there are lots of papers in this topic. Here I'm just mentioning a few of them by Quarteroni and collaborators, Dramond and collaborator, Bafico, Caricino, etc. Now, in comparison, we are interested in biological models where the perfusion of a specific tissue or organ, which for us is the local phenomenon, is studied in correlation to the global features of the surrounding blood circulation. If you never heard of tissue perfusion, it just means the delivery of blood to the capillary bed inside the tissue. Why we're interested in this is because it is known that many pathologies are related to the hemodynamic changes that occur at the microvascular level, where we have small vessels that pierce the tissue, perfusing it with blood. So due to the fact that we have this large number of vessels, each one having small caliber, it is impractical to model each one of them separately using either Stokes or Navier-Stokes. It was done, as I told you, it was done before, but that's usually mostly for the case of large arteries. So instead, to address this issue, we use fluid flow through deformable porous media models, which have been proposed for tissue perfusion, where the blood vessels are modeled as pores within a deformable solid representing the tissue. So let's focus on the local problem. This is where we model fluid flows in deformable porous media. So what are they? These are systems of PDEs that describe this. It's the fluid-solid mixture. So they describe this mixture as a continuum body where we account for the complexity of the microstructure via effective parameters. So for the mathematical setting, I think you can probably see my mouse as I point out. So for the mathematical setting, we work in omega, which is our domain, which is occupied by the fluid-solid mixture. If we take x to be the position vector with respect to a fixed Cartesian reference frame, then by v of xt, we mean the representative elementary volume. So of course, this is made of two parts. We have the solid volume and the fluid volume. As usual, we can introduce the volumetric fraction, where the quotient between the volume of the fluid and the total volume, and this is known as porosity, phi. And of course, the counterpart for the solid, you define it the same. And we work under the assumption of fully saturated mixture. So when you add up the two porosities, they equal to 1. Here's how the fully dynamical poroelastic system looks like. So we have two conservation laws, right? The first equation is known as the momentum balance equation for the elastic displacement U. And the second equation is the mass balance equation for the fluid-solid mixture. So I wrote the system fully just in terms of the two main variables, elastic displacement or solid displacement U and the fluid pressure P. Let me describe everything that shows up here in order. I should say first that this is written under the assumption as full saturation, as I mentioned on the previous slide, but also small deformations for the homogeneous porous medium. Mathematically, that translates into basically a linear Cauchy stress tensor for the elastic part of the equations. So if you work in elasticity, you probably recognize that if I combine the second and third term in the first equation, that's basically minus divergence of the normal linear Cauchy stress tensor of elasticity. So that's why I wrote here on top. You can think of these two terms also as minus divergence of Cauchy stress tensor T sub E, so the elastic stress tensor. Now, of course, we also have sources on the right-hand side. So F stands for an elastic body force. S is a fluid source. In the second equation, note that this is, in fact, in the second equation, this term, this the time differentiated term, this is known as fluid content zeta. And I will talk about more about this on the next slide. In the second term, K stands for permeability, which I will also describe more next. And we have a lot of parameters showing up. So let me describe them in order of appearance. So the first one is rho, which is a strictly positive parameter. This is the density of the porous permeable medium. As usual, lambda E and mu E stand for the Lamé elastic parameters. Alpha is the coupling coefficient in a sense, because as you can see, it shows up in both equations. Here in front of the gradient of the fluid pressure, and in the second equation in front of the solid dilation, right, in front of divergence of U. So this parameter, which is parameter strictly greater than 0, is known as the Biot-Willis constant. It accounts for the pressure deformation coupling. And C naught, greater or equal than 0, this is known as the constraint storage coefficient. It combines the porosity of the medium and the compressibility of the fluid. Now, these equations have lots of applications, including settlements of soils under load, wave propagation in fluid-saturated porous media, as well as, more recently, tissues and organ perfusion. In fact, the whole field of poroelasticity, the development of the field, was inspired by problems in geophysics and petroleum engineering. And this is the scenario where you have fluid that flows through rocks and soil. Mathematically, the first paper that addressed these problems was the paper by Terzaghi in 1925, where he focused on the one-dimensional model. And then it was in around 1940s that Maurice Biot started looking at these problems and really started the development of the field, basically writing the model in 3 dimensions and starting the mathematical development of poroelasticity. That is why if you see Biot equations is synonymous to poroelasticity. So Biot equations, poroelastic system, same thing. And of course, after that, there's lots of literature in the field. Here I'm mentioning just some well-known papers and books by Detournay and Cheng, Barry, Mercer, Settari, Walters, Cusi, Phillips and Wheeler, etc., etc. Again, most of them motivated by geophysical applications, where you have fluid that flows between rocks and soil. But recently, there are many applications coming from biology, medicine, and bioengineering that require the need of this modeling through these systems, because we have fluid flow inside cartilages, bones, and also engineered tissue scaffolds, as well as blood flow through tissues in the human body, like the brain, the liver, and the eye. And I included on the right a picture in the eye, optic nerve head perfusion, because this is what motivated our research initially, and I will give you some more details about it on the next slide. Okay, so before I get there though, on this slide, I started with, this is the general fully dynamical poroelastic system. However, due to the fact that we're focusing on biological and biomechanical applications, there are certain things that we need to update in the system. So the first thing is that inertial effects are negligible. So that means that the first term in the first equation disappears. So now from the mathematical point of view, instead of having a hyperbolic parabolic coupling, now we have an elliptic parabolic coupling, right? And this is known as quasi-static deformation or quasi-static poroelastic system. Now, if you want to think of it on more of an operator framework, okay, how do you put these equations in an operator framework? Then, I can combine the first two terms in the first equation. Of course, think of them as some formal elasticity operator acting on the solid displacement u, so E of u, move the pressure of the gradient of the pressure on the right-hand side. In the second equation, the second term, you can think of it as a diffusion type operator, right? Of course, if k is just a constant, this is like a Laplace of p, right? So let's call this A of p, the diffusion type operator. And then the next thing to take into account is that we know that biological tissues have a mass density close to that of water. Because of this, we are in the scenario of incompressible fluid and solid constituents. Now, what does that mean? If you work in fluids and you hear the word incompressible, you're immediately assuming, okay, divergence equals 0. This is not what we mean in poroelasticity. So when we say incompressible fluid and solid constituents, this means that the solid and the fluid phases cannot undergo volume changes at the microscale. And mathematically, that translates into, and you can find the details in a paper by Detournay and Cheng in 93, into the fact that this constraint storage coefficient C naught becomes 0 and alpha is 1. Okay, so that means that in the second equation, the fluid content, the term that was differentiated, is only dilation, solid dilation, or divergence of u. So then the simplified, formal system can be written in this form here on the bottom. And then what you can do there formally, okay, imagine that, the source f equals 0. That could be easily translated. So imagine that 0, what you can do in the first equation, you can solve for u in terms of p, and then plug them into the second equation. What we've done basically is introduce this pressure to dilation operator, right? So introduce the operator B, which is defined as minus divergence of the inverse of the elastic operator applied to the gradient of the pressure, right? And if we do that, that means that we can write the whole system as one equation, but this is an implicit degenerate evolution equation. Why implicit? Because if you look here, right, we don't just have the time derivative of the state variable as usual. We have the time derivative of an operator applied to the state variable p, right? So that's why it's known as implicit equation. Why degenerate? Because the kernel of b can be non-zero. Okay, so this is a whole class of equations known as implicit degenerate evolution equations, and I will talk about this later when I mention a summary of well-posedness results for these problems. Now, another challenge that comes from the fact that we work with biological structures is what happens, what is the permeability, right? So permeability is not really a constant, right? Of course, mathematically, if we take permeability to be a constant, that simplifies the system. It becomes a linear coupling, right? And from mathematical analysis, it's a much easier problem to deal with. But in applications, K is not really a constant. So we have to consider two scenarios. Either we take it as a given function of space and time, or the more general and realistic one is that the permeability is really a function of the solid dilation. What kind of function? It's a nonlinear function of solid dilation. What kind of function? Well, it depends, right? It depends on the pore architecture as well as properties of the fluid. Then there are two main scenarios that are considered in the literature. So when we have Newtonian fluid that flows between a pack of spherical particles, this is where the Kármán-Kozeny formula is used. So permeability is this quotient between x cubed and 1 minus x squared. And the second scenario is when the fluid flows inside cylindrical pores, and this is when the permeability is taken to be a quadratic function. Okay, the other thing I want to mention here is that usually in the literature you will see the second equation may be written in terms of the discharge velocity, which is really just this product between permeability and the gradient of the fluid pressure with a minus sign. So this is known as discharge velocity. So then the second equation you might see written as the time derivative of the divergence of u plus divergence of discharge velocity. And this is an important quantity, so that's why I wanted to mention it here as well. Anyway, in any case, what we have now, it's a quasi-linearity in the second equation that is not monotone. So of course, this will influence the well-Posner's theory for the systems. Okay, so now that I described the local problem, all this was to introduce the PDE model for the local problem, right? The fluid flows through deformable porous media. Now, how about the global features? How do we account for those, right? So this is a very, schematic picture to illustrate how we're coupling these two physics, right? The physics of the problem. So on one side, we have the BO model, the poroelastic system, and then we have to account for the global features, so we have to introduce this lumped circuit, right? This reduced models. So here, fluid flow through hydraulic networks is described by its analogy with a current flowing through an electric circuit, where we have active sources of voltage and current. This corresponds to pressure and flow rate sources. Resistances correspond to viscous effects, inductances to inertial effects, and capacitances to vessel compliance. So these are known as RCL circuits because they have resistances, inductances, and capacitances. Now, there are two scenarios for the RCL elements, right? Most general case is to consider that they're nonlinear and time varying, and this corresponds to accounting for the vessel deformability and also remodeling. You can also simplify a little bit and assume that the RCL elements are linear and time invariant, and that means that we're assuming that vasculature is compliant but with small deformations and passive. And I should also point out that here, and maybe I'll stay on this slide, so we think about this circuit as we're going to separate it into components. We're going to have the internal circuits, which we called this upsilon tilde, right? When we have N sub R resistors, N sub C capacitors, N sub L inductors, but then we separated the so-called connection, which we call lambda, because this is where we couple, right, the circuit to the PDE, to the BO equations. Now, following the Soren-Ku book from 1969, we can introduce the appropriate state variables for each inductor and capacitor in the circuit. So for each inductor, we have the volumetric flow rate, Q, we call it capital Q, across each inductor. And for each capacitor, we have the pressure difference, and we use capital Pi for that across the capacitor. In the connection, we assume that the capacitor is set to ground, right? So that means here we assume pressure is 0. So then the difference between across this capacitor, we're just going to call that little pi to stand out a little bit, because this is going to be one of the important variables that comes into the coupling with the PD. So that's going to be little pi. Now, the vector of state variables in the lumped hydraulic circuit, this is Y. It has how many components? So the little pi, 1 plus the number of capacitors plus the number of inductors. So 1 plus n sub c plus n sub l. And here's the OD. This is the OD system. The time derivative of y equals a of tyy plus s plus b of q. Let me tell you what each one of these terms represents. So the first one, it's a d by d tensor. This is a. This can be, it could depend on linearly on time, but also on the state variable y. So this is a nonlinear OD. S, it's a d by 1 vector. It represents the sources of pressure and flow rate that may be present in the internal circuit. And the last term is the one that represents the contribution from the connection between the circuit and the BO equations, right? And it has the following structure. So it's a vector that only has the first component non-zero, and that component depends, it's just a constant times Q of T, which is the volumetric flow rate through the connecting resistor. So in the picture, hopefully you can see my pointer here, this is Q. Right, so this is where the PD is connected with the OD through the term Q here. So this is the flow rate through the connecting resistor. Okay, we introduced the PD, we introduced the OD, but of course we have to also mention the associated boundary conditions for the PD, and also what happens at the interface between the two. So let me start with the boundary conditions. So for BO, let's first of all split the boundary into a gamma part and sigma. On sigma is where the PD is connected to the OD, so that's the interface, and gamma is going to be the rest of the boundary. So on the rest of the boundary, the one that's not connected to the OD, we have the following boundary conditions for BO. We had to split again in multiple parts, and think about it first as there's a gamma D and gamma N. Why D and N? Of course, for Dirichlet and Neumann. So on gamma D, we have Dirichlet conditions with respect to U. So as you can see on gamma D, U equals 0. Okay. On gamma N is when we have the Neumann type boundary conditions for the elasticity. So you see here T, which is like a stress tensor, right? Tn equals G. But we also need to have boundary conditions for the fluid, right? And the variables for the fluid are the pressure and the discharge velocity. So that's why we had to split gamma D into two parts. So on gamma dP is where fluid pressure is 0. On gamma dV is when we have a Neumann boundary condition in a sense, because this is grad P dot N, right? So think of it as a Neumann boundary condition for the fluid. So G and psi here, think of them as given sources, given functions of space and time. Now the last two, they are just in the special case when we want to, if we want to simplify this model to 1D, for example, for simulations and so on, and in that case, you need to add these two other conditions. So I will not discuss those now, but those are instrumental for the derivation of the associated one-dimensional model. Okay, so now let's talk about the interface. How are these two things coupled? And this is where the problem is delicate, right? It's subtle because on one side we have the PD, and for PD we need pointwise conditions, but on the other side we have an OD, right? And this just requires mean data. So how do you match those two, right? So first, let's start with boundary condition, not really interface condition for the elastic part, right? So in this case, we assume, let's take U to be 0 on the interface. Of course, other conditions can be accommodated depending what the application is. But this is a simplified one, but we can build on this. Now, what else we know? We know that Poiseuille's law, which is really the equivalent of Ohm's law from circuits, has to hold for the resistor connecting the circuit to the poroelastic medium, so the resistor right here. So what this tells us is that Q, the volumetric flow rate through the resistor, has to be proportional to the difference in pressures, right, at the two ends of the resistor. So on one side we have capital P, which is the pressure at the end connecting to BO, and then little pi, which I mentioned before. So Q equals P minus pi over R being the resistance. Like it's a constant. Okay? Now, we also need to have continuity of pressures at the interface, right? And accordingly, once we assume continuity of pressure, we need to adjust the interface condition on the discharge velocity in order to make sure that Poisson's law is satisfied. Okay, so they're coupled in a sense. So there are two things we consider, two cases we considered here. So one way to do that, okay, continuity of pressure, well, let's assume that the pressure is equal, right? So let's assume that capital P of T equals the BO pressure, which is little p of x and t. Well, if we have this assumption, then in order for Ohm's law to be satisfied, then we need to assume that the volumetric flow rate Q has this non-local, it's in a sense, it's a non-local term on the interface, right? Because it has to be the integral over the interface of discharge fluid velocity dot n. Now, the second scenario is when we're going to assume, okay, let's take the pressure at the this left hand of the circuit. Let's take it to be the average of the BO pressure on the interface. Okay, if we do this, then we really get more point-wise type of conditions for in order to satisfy Ohm's law. So this is when we get that K is just a constant, K V dot N equals fluid pressure minus little pi. Okay? And we call this the case of point-wise pressure condition versus integral pressure condition based on this assumption of how we maintain continuity of pressures at the interface. Now, what kind of condition, right? The choice of which interface conditions to adopt, of course, this is part of the modeling process and is dictated by the application. For our application, which I will discuss in a little bit, the second case, the integral pressure conditions, makes more sense. We do have a paper, a recent one, where we numerically will look at comparing the solutions between the two scenarios, right? And why we think for us case 2 is more relevant, because as you compare the two, you notice that in the pointwise pressure condition, really this imposes a really big constraint on the BO pressure, right? Because we're assuming that the BO pressure at the interface does not depend in space, right? So that's a constraint for the BO pressure on the interface. The other thing I want to point out here is that these integral pressure conditions, okay, are very similar to this, and they're so-called natural conditions or natural interface conditions that appeared in the previous papers when I mentioned those papers focused on physiological flows, where they have Navier-Stokes-Torsorg equations coupled with lumped circuits, right? So these are very similar to those conditions, that interface conditions that they had. So you can see that in a paper by Quarteroni and Veneziani, which was based on this paper by Haywood, Raneker, and Turek, where they were found this type of natural interface conditions. Okay, so now let me mention the application and how we started working on these models. So we were interested in perfusion in the optic nerve head inside the eye and its connection to the development of neurodegenerative eye diseases, in particular glaucoma, right? This is, if you've never heard of this, this is it's a group of diseases that basically leads to irreversible loss of vision. And the way you see here on the right is 4 pictures. It shows the progression of the disease. So basically, the vision is lost from the sides toward the middle. And in extreme glaucoma, the person only can see basically through a tiny tube in the middle of their eye. This is the leading cause of irreversible blindness in the U.S. and the world. Currently, elevated intraocular pressure, which is the pressure inside the eye globe, in short IOP, is the only treatable risk factor for this disease. And how they treat it, they recommend eye drops, and if eye drops don't work, then they recommend some laser surgeries and so on. I I zoomed in here on the optic nerve head for you to get to see a little easier what's inside, because what they know at this point is that it is believed that it's the biomechanics of this deformable porous tissue at the base of the optic nerve head. In the picture, this grayish thing here, known as the lamina cribrosa, which plays an important role in the development of the disease. So one of the main roles of lamina cribrosa is to maintain the pressure difference between the intraocular pressure, which is the pressure in the eye globe, and this pressure in the back of the optic nerve head, known as the RLTP. Now, it is known that changes in the IOP are normal, they're physiological. Like if you rub your eye, IOP changes, if you stand up suddenly, IOP changes, and so on. However, there are many studies that indicate that having chronic IOP elevation, this induces significant structural changes in this tissue, in the lamina cribrosa, okay? And as I told you, up to date, this IOP is the only treatable risk factor for glaucoma. However, there are many individuals with elevated IOP who never develop glaucoma, while at the same time, about a quarter of IOP-treated patients progress to blindness. So clearly, this is significant evidence that there are other factors that are involved in the disease. IOP is not the only risk factor here. So what did we do? So first, and this started a long time ago, right? So the first thing we did was, okay, let's focus on the local problem. Since we know it's the biomechanics of the lamina cribrosa that does something, right? Let's focus on that. And this is a deformable porous tissue, right? So we can use poroelastic systems to model it. However, because we know that tissues exhibit both elastic and viscoelastic behaviors, right? Because they're made of both elastin and collagen, let's include viscoelasticity into the models, right? And that's important because we also know, it is known that structural viscoelasticity decreases with age and disease. I think I, for one, know that, right? I mean, as we grow older, the production of collagen in our body dramatically decreases, right? Unfortunately. And it's also known that collagen structural changes have been found in patients with glaucoma. Okay, so how mathematically, what do we do? So I already introduced the poroelastic system, right? This is on the left. We're going to include structural viscoelasticity. How did we do that? We chose the Kelvin-Voigt type of viscoelasticity. So basically, we're adding another stress tensor, same formula as the usual linear stress tensor for elasticity, but instead of depending on mu, depends on u sub t. Okay? So then the total stress tensor for the mixture has three components. The usual one you've seen before, the elastic stress tensor, but now we're adding this term and we're incorporating a parameter delta in front of it, greater or equal than 0, to indicate the extent to which our model includes these viscoelastic effects. So if I take delta to be 0, it's gone and I am back in the purely poroelastic scenario. If delta is positive, then I'm accounting for structural viscoelasticity in the system. And this is a paper we started this, as I told you, about 10 years ago. And the first paper we wrote on this was a paper with Giovanna Guidoboni from University of Maine, Riccardo Sacco from Politecnico di Milano, and Justin Webster, who is now at University of Maryland, BC. And before I tell you what we did in that paper, I should give you a short summary of what is the literature on well-postness for poroelastic systems. So I split this into two parts because it depends on do you have constant permeability and therefore you work on a linear system, or permeability is a nonlinear function and then you have nonlinear coupling, nonlinear poroelasticity. So of course we start with linear scenario. So permeability is just a constant and there were no viscoelastic effects accounted for, right? So delta is 0. This is pure poroelastic system. The first paper in our knowledge that dealt with well-postness for the system is a paper by Orio and Sanchez Palencia in 1977. In this paper, though, they focused on compressible constituents. So if you remember, that means that this constrained storage coefficient has to be strictly greater than 0. There were no sources, and they had homogeneous Dirichlet boundary conditions for both U and P, which, of course, as you expect, simplified the analysis quite a lot. Okay, why is this very different? So remember I explained to you that the whole system can be written as one implicit degenerate evolution equation that looks like time derivative of BP plus AP equals S. Now, when you add compressible constituents, the first term is no longer just BP, but it looks like constant times the identity operator plus B instead of just B alone. And that is much nicer because this new operator is coercive and invertible on L2, a property which B alone does not have. So from the well-posedness theory, this makes it much easier to deal with the problem because you just invert and you're back in the usual framework of parabolic equations. Okay. After that, there's a paper by Zenitek in '84. He focuses on the two-dimensional scenario, and he studies weak solutions using Roth's method, meaning he discretizes in both space and time. And it's around 2000 when Showalter considers the problem with general boundary conditions, and he really develops the whole semi-group theory for implicit evolution equations, okay? And then applies the theory to this specific system and discusses both strong and weak solutions. He follows that with a paper next year in 2001, where instead of having constant permeability, he has nonlinear permeability, but this is the case where the permeability is taken as a nonlinear function of the fluid pressure, which was motivated by geophysical applications, in such a way that you preserve a monotone structure in the problem. And therefore, you fall back into the theory that was developed before, the semi-group monotone theory for implicit evolution equations. The first paper that dealt with a nonlinear permeability that was dependent on solid dilation is a paper by Kaochen and Meyer in 2013. However, they had compressible constituents, so C naught is strictly greater than 0, and I already pointed how that makes the problem easier to deal with. And they also simplified the boundary condition to just homogeneous Dirichlet boundary conditions for both U and P. So now in comparison, in our paper, we wanted to, driven by the application we had in mind, right? We wanted to account for nonlinear coupling, right? So K, nonlinear function of dilation. So there's no monotonicity in the problem. You cannot use the semi-group theory from before. We want to focus on incompressible constituents. And what that means basically destroys the parabolic nature of the second equation because you no longer have C0 P sub T. And also include the more realistic non-homogeneous mixed boundary condition. And this, as you know, if you work in elasticity, and we allowed basically also the Dirichlet and Neumann parts to touch, okay? So then it means that you lose full elliptic regularity for the solid displacement. And the other thing, we wanted to make a comparison between the purely elastic case and the viscoelastic case. So what happens when we include structure of viscoelasticity in the problem? And here's the summary, and kind of the main thing that we discovered was that, of course, the presence of viscoelasticity changes the situation. In what sense? And here I color-coded to make it easier to follow. So if we include viscoelasticity, these were all sources. F was the distributed source in the first equation. G was the Neumann boundary condition for elasticity. So T dot N equal G. So start with F L2 L2, G L2 H half on the boundary. You get, weak solution. You get the existence of a viscoelastic solution. And note that, of course, you get H1 in time, H1 in space. Why H1 in time? Because in a sense, when we added that Kelvin-Voigt type of viscoelasticity, in a sense, you're introducing you're introducing something depending on U sub T, okay? And that gives you higher regularity in time. And fluid pressure, L2 in time, H1 in space. Now, in comparison, when there's no viscoelasticity, you need higher regularity in time for both sources related to elasticity. So H1 in time for F, L2 in space, G also H1 in time, HF, in order to get weak solution, which is only L2 in time, H1 in space, and pressure L2 in time, H1 in space. I'm not going to go through the details. What the immediate question to this, as you see, so I only said there exists solution. I didn't say anything about uniqueness. And how did we prove this? Well, we had to use discretization. So in a sense, we followed the idea of Zenitsek to discretize in both space and time, and then had to build up, of course, upon that with different many strategies. So the question is, why not use a fixed point strategy in this nonlinear coupling? And do you have uniqueness of solution? Which, of course, we also thought about for a long time. And it turns out that these two questions are basically the same question. They're very related. So let me point out why. So let me start with uniqueness of weak solution. So if you have constant permeability, you get unique, weak solutions are unique. And that was, done from that first paper I mentioned by Orio and Sanchez Palencia. However, as soon as you move from constant permeability to even a given function of space and time, the problem becomes non-trivial, okay? Uniqueness results are available, for example, in the paper by Showalter, but you need to add additional assumptions on the permeability. So you need the time derivative of permeability to be L1 in time, L infinity in space. Why is that? What's the crux of the matter is the following. We do not have energy estimates for arbitrary weak solutions. They're only available for constructed solutions, right, as limits of approximates. And the main issue is the multipliers. So in the two equations, even though this is elliptic parabolic coupling, so the first term, the one that had UTT, is no longer there. However, UT remains the desired multiplier in the first equation, along with P in the second, in order to deal with the coupling between the two terms, okay? However, you don't have regularity on UT to use it as a multiplier. So you need to go to the other, boost the level. So use U and integral of P as multipliers. When you do that, right, so in this second term, I'm multiplying with an integral in P. The way to move forward is to be able to write the term as a total derivative. So if I want to write the term as a total derivative, you understand that that's when I need to put assumptions on the time derivative of the permeability. That's the idea. And that's exactly the main impediment to using fixed point methods. Because to build a fixed point method, that means instead of divergence of U and K, I need to put a Z there, okay? But when you build this map and you want to show it has a fixed point, I cannot put assumptions on permeability, which depends on D, but that implicitly depends on the solution. So you cannot really do that. So that's why the fixed point method could not be used. Okay, so because we thought about this so long, and we wanted to have some more answers related to this, what we figured out is, okay, so let's work with multi-valued functions. Okay, so first paper, this is with Justin, and a paper that appeared in JD in 2021, is we use the counterpart of Schauder fixed point theorem for correspondences. Correspondences are multi-value functions, and the theorem is known as the Bodenblast-Carling theorem, okay? So we focused here on, note that we had to simplify the system a little bit. We had to assume, we simplified the boundary condition to just homogeneous Dirichlet boundary conditions, but we showed basically that we can use the fixed point method if we work with multi-value functions, basically in a similar way to a Schauder fixed point theorem. So that was one way to deal with that. However, that we weren't satisfied with that, right? So the next point is can we show uniqueness of weak solution for a linearization of the system where the permeability is a function, just K of some Z, where Z is given, without imposing additional assumptions on the permeability. And this we were able to answer in 2022, again with Justin Webster and Boris Muha. And this is a paper in nonlinear analysis real-world applications, where we were able to prove uniqueness of weak solution without any additional assumption on permeability. Again, on a little simplified, we had to simplify the boundary conditions here. And after, right, you can just apply, once I have this new result, then I can just really apply Schauder's theorem to get existence of solution for the nonlinear coupling. Okay, I will skip the details here and the strategy, all that. Just to come back to, this is the first result I presented from the first paper, the the most general system, right? Where we had the non-homogeneous mixed boundary condition and so on. And when we found this, of course, it brought even more questions, right? Because based on this, like, what if I have only L2 regularity in time, right, for both F and G, and I don't have any viscoelasticity? What does it really mean in this elastic case? Does it mean that the solution exists, but it's our approach that does not see it? Or does it really mean that there's a blow up in the solution, right? And if there's a blow up, who blows up, right? Which energy blows up? Is it the energy associated with the solid displacement, or is it the energy associated with the fluid pressure, right? So this is when we did some numerical simulations. We simplified the system to one dimension, and we took some here I just focused on the boundary source G. So basically the idea is the following: if you need G to be H1 in time, let's take a G that's not continuous in time, right? You're in one dimension, so H1 in time is continuous in time. So let's start with poroelastic system and take a source that's not continuous in time and see what happens to the energies in the system. Okay, so that's what we did. So here we took a G that basically was a step function, 0 and then switched to 1 at point 0.75, and then from 1 down to 0 at 1.25. And what we notice is that exactly at the time of discontinuities for the source G, we have these sharp peaks that appear in the energy associated with the fluid in BO. Okay, and you can see that the peaks increase as you let delta T go to 0. So clearly a lack of time regularity in the source G reflects into a lack of regularity in the fluid energy. If you add viscoelasticity, so if delta equals 1, notice that the peaks are smoothed out in a sense, right? The peaks are no longer there. Okay, so but this, this is just this numerical simulation. They're not really a proof, right? It just gives you hints of what's happening. But if you're in one dimension, you can actually explicitly solve the system. It's not nice, it's just tedious work. Okay, nothing hard. You can use that in your undergraduate PDE classes, give them as a homework, solve explicitly, and the solution you can solve. You have the Fourier solution, and then we can actually see that the discharge velocity blows up. It goes to infinity if the boundary condition is not continuous in time and there's no viscoelasticity in the system. Okay, and we have a couple of papers in I think one in 18, one in 19, where we looked at this in detail. So based on this, we had a hypothesis concerning the causes of damage in biological tissues, namely lack of structural viscoelasticity in combination with abrupt time variation in mechanical loading. So basically, when you have discontinuous sources, this leads to blow up in the fluid velocity in the porous medium, which creates microstructural damage. And this kind of makes sense, right, from the application point of view, because there is experimental and clinical evidence that shows that loss of viscoelastic tissue has been associated with various pathological conditions, including glaucoma, which is what motivated our analysis, but also other ones like osteoporosis, renal disease, Alzheimer, etc. So the ultimate goal for us became to, okay, can we provide some practical direction of how to control the biomechanical response of this mixture? Right? And mathematically, what does it mean? We need to develop control and optimization problems related to the system. And there's a bunch of papers in that area, but that's not the focus of the talk today, right? But that's one way to proceed, is to look at control problems related to this. The other thing for us was to understand that even though this is an eye disease, right? It's a biomechanic of a specific tissue inside the optic nerve head that is connected to the development of glaucoma. However, we cannot just ignore the global features, right? then there are multiple studies that says that blood pressure is also a risk for glaucoma, right? So we should somehow account for that as well. If you're interested, there's a very nice webinar, which I think you can still find online, by Professor Alan Harris, he worked in glaucoma for decades. He's also on the board of directors for the Glaucoma Foundation, and he gave a very broad audience webinar on this body-eye relationship, and that's very interesting, and you can listen to that if you're interested. So this is what motivated us to not only focus on the local problem, but to look at this multi-physics coupling, right, where we have the PD, but we also have the OD to account for the blood pressure in the body. And these are some of the papers that we have so far. And this brings me back to the system, right, which now I put everything in one slide, but I already introduced before, right? I have the BO equations on the left. I have the ODE system on the right. We, of course, have the interface condition between the two. And the first, what we've done so far, right, is we have some analysis, some well-posedness, and some numerical solutions, right? So let me start with the well-posedness. So what we have in this paper, it should say it's accepted and it's in press from 2024. This is where we showed local existence of weak solution for this multi-scale interface coupling. Okay, so let me go directly to the theorem. So as before, note that I have to maintain this regularity, the H1 regularity in time, and for both F and G, because this is the poroelastic case. There's no viscoelasticity here. This is the poroelasticity coupled with OD. So under these assumptions, and we can show that there exists a time, which is t tilde here and 0t, such that we have a weak solution for the coupling. So let me briefly explain the strategy. So kind of a big picture of the strategy. This is a fixed point method. Okay, so how do you build a fixed point? So basically, let's start with the ball. I call it BM0T. This is in L infinity, so nominal infinity of Z is bounded by M. So we basically, what we do first is start with the BO equation, right? Take the BO equations with their boundary condition, and also take consider the interface condition as boundary condition given little pi, right? Because little pi is the first component of Z. So basically, given little pi, solve BO. This is the first operator. So we're given little pi, we're solving BO. If we solve BO, of course, we get U and P, but all we need is P, the fluid pressure. Once I have little p, I can, of course, take its average on the interface and find capital P, right? If I have capital P, then through the Ohm's law, it gives me the relation between capital P and Q. And once I have Q, I can plug it into the ODE, right? That's the idea. So then you plug Q into the ODE, you solve the ODE, which will give you the state variable Y. This is the vector of states for the ODE. And therefore, what you do now, by composing these two operators, we get our operator T. So this is the composition LOD with LBO, which is, we call T of Z equals Y. And of course, at this point, what's my goal? I want to show that this has a fixed point on the ball BM of 0T, right? This is the usual strategy, fixed point method. But hopefully the picture makes it okay. The strategy here, without going into much detail, the first is what? I want to show that there exists a time T tilde such that the ball is invariant under my operator. And the second thing is I want to show, of course, that the operator is compact on the ball, right? BM of 0 T tilde. What is this based on? So the first part here is based on, of course, all the theory that I knew already, right, for BO and ODs. BO that we've done before, or the poroelastic theory, because I need energy estimates and then how they connect. So from that, combining the energy estimates, we can obtain basically an estimate for the ODE states, right? Which looks like this. And the idea here is that, think of it as two curves, basically. On the right-hand side, because here we start with the initial condition less than m, right? So this in time is a monotonely increasing curve that goes up. And then if you look at this curve that's m squared times exponential to the minus power of the first, this is a curve that goes down, right? So it has to exist, there must be a time where these two curves intersect based on where you start with this one and where the other one comes down. That's the kind of the big picture idea, okay? So there exists a time where you can get this inequality, and therefore you get the y of t is in m. So you show the invariance of the ball under the operator. And then to show compactness here, you since we know that both operators LOD and LBO are continuous, you get that the composition is continuous. So then all I have to show is that the range of the operator is relatively compact. And for that, so all this is based on the what's it called, Artela-Ascoli theorem, right? And then once we have compactness by the usual Schauder fixed point theorem, there exists a solution such that Ty is y. Note here that what I'm not mentioning, of course, is uniqueness, because usually when you apply Schauder, you do not get uniqueness, right? So this is just a local existence of weak solution. So this is the most recent result. We also have numerical results, but maybe I will leave them for some other time as I'm running out of space. Not of space, I'm running out of time. So just one thing to point out here, for numerical solutions, what we wanted to do, basically, we wanted to, maybe I go to this slide, we used two approaches and we wanted to compare what happens between functional iterations and an operator splitting method. Because while the local existence, as I showed you, was based on a fixed point method, when you do functional iterations, which are fixed point methods in a sense, it turned out that it didn't work very well, because when you think about algorithms, right, you first look at the energy, the physical energy of your problem, right? You get an energy for the problem, and what's important here is that we actually get a dissipative system. If you take the sources to be zero, you get a dissipative system where you have this term here that's a positive term on the left hand side coming from the connection between the BO and the circuit, and that's important. And the question now is, do you preserve this energy when you discretize, right, at the discrete level? And it turns out that using functional iterations does not preserve the energy. So there's certain issues there that do not work, because there's a right, when you decouple them, you lose that nice matching at the interface. That's the whole idea. So that's why instead of using functional iterations, we proposed using an operator splitting algorithm, because this is an energy based method. It preserves the energy, and we were able to show, because for operator splitting method, there's no you don't have to worry about convergence, but you have to talk about stability. And we were able to show that this method is unconditionally stable with respect to the time step, and it's all based on the fact that it preserves the energy at the discrete level. Okay, I'm gonna stop. I'm sorry. Just the last slide is to acknowledge all the groups that were involved in this and all the work for the last 10 years or so related to poroelasticity, to multi-scale interface couplings. And we also have work where we couple poroelasticity with Stokes and flows and so on. And of course, to acknowledge the support from NSF. And thank you all for joining today. It is Friday, so just a little bit more, and then the weekend is here. Thank you.
Thanks, Lorena, for your interesting talk. Are there some questions or comments? We have just a few minutes before the other talk. You can write in the chat if you have some question. So just a curiosity, Lorena, are there some results if you consider a delay or a memory return?
So far, no, but I would be more than happy to work with you, Jenny, with adding some memory terms.
I will be happy to.
Yeah. Thank you.
Okay. Are there other comments, questions? If not, thanks again, Lorena.
Thank you very much.
And the next talk is in 2 minutes. It will be 2 minutes by Enrique Zuazua. I think that it is already here. Yes. Ciao, Enrique. I think that you can share your screen and probably Duvan will introduce you. If
Professor Enrique. Hello, hello.
Enrique, you have the microphone off. You have to open.
Do you see the slides?
Yes.
Okay. Yeah.
Yes.
Sorry, someone was talking to me. Yeah.
Oh,
Okay.
hi, Professor.
Hello. Nice to meet you.
I'm Brian, Professor. We have been
Oh, hello, Brian.
conversations by email.
Yeah. Thank you for organizing all this so well.
Oh, thank you for participating and for contributing. We are trying to fix some issues with the sound at the auditorium because we want to present your talk from there, but if you give me, you and all the participants
How
and give
long
me
do I have to talk? Is 40 minutes or 35? I don't remember.
from 45 to 50 minutes and
Okay.
10 or 15 minutes
Very good.
for questions.
Yeah, keep it in mind. Yeah, thank you.
Just give me 1 minute more. Okay, apparently we could resolve the sound problem at the auditorium. Professor, is okay to start in just 3 or 4 minutes?
When you want, I'm here. No rush.
Okay. Okay. Diana or Juan, I will ask you to mute your microphone.
Okay. Okay.
It's okay.
Okay. Okay, let's wait maybe 1 minute. 1 minute. Okay, so thank you very much to all the participants for joining us in virtual way and also in person here in the Pontificia Universidad Javeriana. It's my great pleasure, my really great pleasure to introduce Professor Enrique Suazua, who is a leading expert in applied mathematics, focusing in partial differential equations, control theory, numerical analysis, and machine learning. Professor Suazua holds the position of Chair of Applied Analysis at the Friedrich Alexander Universität in Erlangen-Nuremberg, FIU, in Germany, and leads the Alexander von Humboldt Professorship. He also is the scientific director of the Chair of Computational Mathematics at the Deusto Foundation in Bilbao, in Spain. Throughout his career, Professor Suazua has won several important prizes and awards, such as the Euskadi Prize for Science and Technology from the Basque Country in 2006, the National Julio Rey Pastor Prize from Spain in 2007, and 3 European Research Council Advanced Grants in 2010, 2016, and 2022. And also the WT and Idalia Ray Prize from the Society ICMAM in 2022. Professor Suazua also was an invited speaker in the Control and Optimization section at the International Congress of Mathematicians in 2006 in Madrid. With over 300 published papers and scientific reports, Professor Suazua's work has a big impact in mathematics. He has supervised more than 30 PhD students and has helped many master students and postdoctoral researchers. Professor Suazua also is co-editor-in-chief of the journal Mathematical Control and Related Fields and Advanced in Continuous and Discrete Models. He also serves on the editorial boards of many journals and works with many scientific committees. Just to finalize the presentation of the amazing career of Professor Suazua, just let me say that he also helped to develop applied mathematics in Spain. He was the first manager for mathematics of the Spanish National Research Plan from 1999 to 2002, and the founding scientific director of the Basque Center for Applied Mathematics, BICAM. So thank you very much, Professor Enrique Suazua, for accepting our invitation, and please start.
Thank you, Duvan. Thank you all, ICMAM, for this very kind invitation. It's for me a great pleasure to be the opportunity to be once more with you. Duvan is one of our closest collaborators. You were visiting us already a few years ago in Bilbao. Later last spring, you were helping us to organize the workshop mainly devoted to the cooperation with Latin America in the broad field of applied mathematics and machine learning. And for me, it's always a great pleasure to be here with you. So this is a talk on the interface of control and machine learning. Some of you have already maybe heard a similar talk that I have delivered on this topic in recent years. But I like to, speak on this again and again, because I think this is really a very important topic, very fascinating, and I think is full of opportunities for all of us. There is already actually a very intense research on the understanding of the magnificent behavior of machine learning, employing Fourier analysis techniques, compressed sensing, stochastics, probability, statistics, high dimensional functional analysis. So the problem can be tackled from very many different perspectives. And there is definitely plenty of room for new discoveries. And I think it's a topic that certainly is a very, very good one, especially for young people, PhD students, postdoc, or even more senior people that once having achieved some level of consolidation on a given topic are willing to explore other fields. So needless to say, the context we all know more or less what it is. So we are nowadays surrounded by artificial intelligence. Even those that we never were particularly interested in these tools, well, they arrive and now they are part of our lives. So some of you, the more senior members in this audience, maybe recall that, Google, for instance, appeared, I don't remember exactly, maybe around year 2000, 20, 25 years ago. Before that, there was no Google, there was not Google search. So one could use, of course, internet and browse, but one needed a specific address that one was, and then you have to keep all the addresses of the laboratories or the individuals or the nets or the journal you were visiting. You needed to know them in the agenda without error if you wanted to really find this page. Now you don't need to do that anymore. If I am interested on the, I don't know, visiting, for instance, the last issue of the AMS journal Mathematics of Computation, I simply Google Mathematics of Computation AMS, and boom, the journal will immediately emerge, right? So I don't need to have the URL address in order to find the items. That was a revolution. And then, it appeared. I remember very well the first time I heard about Google. I was visiting the University of Nice, and I was in the library asking for some reference. And then the technician working in the library told me, let me Google. And I said, what does it mean, Google? I mean, that was the first time I heard this word. Now, of course, since 25 years, it's an instrument, a tool that we employ daily on our work. A couple of years ago, the same happened with ChatGPT. You see the logo on the right. Now with ChatGPT, you can do many more things. So ChatGPT is like the merging, the fusion of the Wikipedia, of Google, of translators of text, many correctors of text. So it has integrated the functionality of many other softwares. As you know, the acronym ChatGPT, G is for Generative Pre-trained Transformer. Transformer is the big architecture that has been built in order to achieve all these multitask. Generative, it means that not only it can simply translate or find as Google can do, or copy paste from the Wikipedia information that people have previously edited, but it has indeed the capacity of generating. This is why it's becoming so useful. You have to, I don't know, complain because there is no sufficient parking place for bicycles in the student residence in which you are living, and you want to send a letter to the chancellor in charge of the facilities of the university or the campus. You can ask ChatGPT to say, can you please draft a polite letter to our chancellor asking him for more parking places for the bicycles in our campus? And immediately you will get a one-page, very nicely drafted letter, right? So it's generative. So it's one step further, much beyond what you could do before with the Wikipedia or with Google search. So this is already in-house. We can, for free, employ the ChatGPT version 3. If you want to make a more professional use, I don't know, because you are editing images or because you are writing complex computational codes and you want ChatGPT to assist you on this, maybe you can go to the subscription of ChatGPT 4, then you will pay a little and you will have a much better service. Okay, ChatGPT is here. This is on our daily life. But artificial intelligence is also very much playing an important role in other more ambitious scientific endeavors. For instance, you see articles every year, every few months, we see new articles in which the newspapers very often, broadly broadcasted by the daily newspapers, they explain how artificial intelligence has been used for this or for that. Actually, the last physics Nobel Prizes was devoted to people that precisely made breakthroughs in artificial intelligence that then had been of very much use either for, I don't know, the unfolding of proteins or other applications in material sciences, in health, or so now it's part of our scientific daily activity as well. So here you see on the left this article about the use of predictive control for fusion plasma by digital twins. So you see a few keywords here. Fusion plasma, well, a complex physical process. Digital twin is precisely a computer environment in which you combine models, numerical solvers, data, statistics, and artificial intelligence to manage, this complex physical process that you could not simply do by using classical PD analysis and numerical mathematics, right? And then, of course, the idea of predictive control, very closely related to reinforcement learning, which is one of the most successful branches of machine learning, that very much tries to mimic the way we humans learn, right? So we learn by reinforcement, right? So when you if you offer me a new I don't know, a new computer, for instance, I will not read all the booklet of information about how this computer works. I will simply turn it on and start operating. And by operating, I will see whether the classical operations I am used to are still working. If they work, I will employ them. In case they don't work, I will try to find out how to slightly change my test strategy to make them work. And then I will also explore the other, possibilities that this new computer offers, like, I don't know, splitting the screen or editing text in different ways, using a pen or others, right? So we humans live and grow and learn and evolve and run our lives based on this principle of reinforcement learning, which is very close to predictive control. Predictive control meaning you predict a given scenario and then you control and you act. But maybe because the scenario was not exactly the one you predicted, maybe the output you got out of your control action is not exactly the one you wanted or the one you expected, then you improve your prediction and you act again. right? And this is what we do when we are traveling. We are using the maps on internet and level by level, you know, zigzagging, but more or less in a nearly optimal manner, we can go from origin to destination. And then you see other fantastic applications, like, for instance, the use of these precisely reinforcement learning techniques in order to, for instance, multiply big matrices. Of course, matrix multiplication is very easy, right? If you matrices one by one are particularly simple, it's just multiply numbers, A times B. If you give me 2 by 2 matrices, then it's also very easy to multiply A11 times B11 plus A12 plus B12 and so on. But as soon as you consider matrices that are big, certainly this is not the exercise you want to, you want to do during this weekend, right? So you don't want to spend your weekend multiplying 2 matrices, 100 by 100, full of numbers. So we need a computer in order to do that. And this is not only a game. It can be a game, but it's not only a game, because, as you know, in the end, every computational code, whatever the challenge is, even if it is about solving these 3-dimensional Navier-Stokes equations that we still don't know how to solve completely from an analysis perspective, right? So the Cauchy problem for the 3D Navier-Stokes is still one of the millennium problems, not completely open. We still don't have a complete understanding of the good Hilbert or Banach space in which we can guarantee existence, uniqueness, and persistency of solutions. But if you want to do a numerical approximation of this model, it's very nonlinear. It will be very high dimensional. We'll have to do many iterations, use finite volumes in space, maybe time integration in time. But eventually, when you look how this code is unfolded, you will realize that in the very end, everything is about, multiplying or adding matrices. So matrix multiplication is one of the fundamental tools of computational mathematics, maybe the most fundamental one. And you see that precisely because of being so strategic, so central in all sciences, machine learning is also being employed to help humans on this by finding faster and more efficient algorithms. So machine learning and artificial intelligence is here at all scales, from the very daily use of ChatGPT for routine work to the highest level, challenging applications of our society, health, energy, transportation, astronautics, all kind of finances, and so on. And then there is also more technical use at the level of accelerating computational algorithms, something that is a must if we want to more successfully ambition to tackle more complex applications, okay? So then this all opens, as I said in the very beginning, a huge universe of mathematical questions that need not only of the expertise of one discipline, but from all of them, in particular, those related with dynamical systems, PDEs, numerical analysis, harmonic analysis, and certainly optimization and control. Now, when you approach this field, you realize that it is so rich. Somehow, ChatGPT has generated a new universe. By the way, ChatGPT is so generative that sometimes it can also generate fictitious realities. So, for instance, you have to be careful with ChatGPT. I did it recently. You can ask to ChatGPT to tell you about the state of the art on a specific topic of mathematics. You can ask ChatGPT to, I prefer not to do it in real time. You can maybe do it in your own cell. Ask ChatGPT, for instance, to tell you, please tell me what is the state of the art on the uncertainty principle. And you will be amazed. It will tell you what is the origin, Heisenberg, quantum physics. Then it will give you the statement of the uncertainty principle in terms of this celebrated inequality where you can somehow balance the L2 norm of the state and the Fourier and the concentration and so on. And then they will give you some references, maybe ordered in an historical manner. But be careful, because sometimes ChatGPT will interpolate data from the internet and might end up giving you a reference that doesn't exist. Right? So maybe ChatGPT will know that maybe some of these big names in harmonic analysis, say Calderon, maybe it will take the name of Calderon and put a title, interpolating titles about sharp inequalities for the uncertainty principle, and then maybe we'll take a prototypical journal for this kind of paper, like the Annals of Mathematics, and then the year, we'll guess the year, and when you will go to the internet, to Mathsinet, or to the journal in order to find this reference, you will find that it doesn't actually exist. So this is the generative capacity of ChatGPT, which has also its risk, right? So you can generate true things, but you can also generate fictitious, fake things. Depending on how relevant it is for you, you have to be careful. But certainly, you cannot use blinded ChatGPT to build the bibliography for your next paper, right? You can maybe get orientations, get some tips. Maybe it helps you finding papers you could not think of. But when you are going to build your bibliography, you better go to Mathsinet and then pick one by one, because you know that those in Mathsinet have been tested, have been referred, have been summarized by experts, and that there is a technical body of experts in bibliometrics that have taken the care of building this bibliography carefully. Okay? So then there are many questions that can be addressed and that need to be addressed from a mathematical perspective. And this, as I said several times before, requires the efforts, combined efforts of different disciplines. One of them is, why does it work? I mean, it does work to a large extent, right? Maybe you get some fake references, but still it works very well. Now, can I use neural network in my own field? For instance, if I am an expert in partial differential equations and numerical analysis, can I use neural networks to solve PDEs? Right? This is a completely different question. One is understanding why it works, and the second one is how I use it. And then the third one is maybe, how can I use neural networks together with all I know before in order to maybe generate new fields of mathematics? Like, for instance, this field of PDE plus D that little by little is emerging and is shaping and is invading our activity as well. PDE plus D, referring to PDE, as you all know, partial differential equations, plus D, D for data. So how do we, other than following the classical books in mechanics in which they will tell us, listen, the fundamental equations are those of heat, wave, Schrodinger, Maxwell, right? Navier-Stokes, Stokes, and so on, depending on the physical context, on the application you are considering. And then these are the tools to solve them. Nowadays, we often face applications in which we have data, but this doesn't really clearly correspond to a classical equation. If I want to understand, how people on campus, when approaching last time, get to the canteen, well, probably this is maybe related to some particle dynamics, but there is not a clear equation to deal with this. I have to very much rely on statistics, on the data I have. And then the field of PDE plus D is precisely trying to figure out what is the most smart manner of integrating this data-driven knowledge into the already model-inspired methodologies we have developed along centuries, combining mechanics, analysis, and numerical analysis, dynamical systems, and a number of fields, right? Very good. So Now, when we approach machine learning, the first thing we have to realize is that machine learning has created a new artificial world, right? So the world we are dealing with in artificial intelligence is not the world of the winds or of the rivers or of the buildings that we are used to work with in the context of elasticity, viscoelasticity, fluid mechanics, as in the previous talk by Lorena. So this is an artificial world. So this artificial world is, though, created in order to deal with real data. So how do we mathematically address this challenge of building an artificial world that will be able to integrate data? The data can be about, I don't know, the behavior of humans. So how humans in a given country, what is the consumption of coffee, for instance, right? And then they will discover that, oh, mathematicians drink a lot, right, of coffee. Okay, so how the behavior of different individuals with respect to consumption of coffee and the pattern of consumption of coffee, the intensity, the frequency, and so on, how is this distributed in the population? Well, what you do is you collect data, right? And then out of this data, you try to build an algebraic model, a function that will be able to interpolate all this data, okay? So you can do it using maybe classical polynomial interpolation or so, but of course, this will be extremely complex when you are considering data that are distributed in an heterogeneous manner. It can be of different nature. You can have data that are vectorial, like for instance, the blood test. Whenever we do go to the hospital and we do a blood test, we get, I don't know, 20 or 50 different parameters. These are vectorial data of actually different dimensions. Some of them can only be positive, but others can be also negative. There are different ranges of validity for different parameters. So this is extremely complex. So now what machine learning has done is to combine two very elementary ideas in a very clever manner to be able to guarantee that there are tools that are able to absorb all this information. And the best example is precisely the transformers of ChatGPT that are giant models like this, right? That were able to understand, read all the Wikipedia, see all the films, watch all the paintings, to the point that you can ask to ChatGPT, please draw the picture of a mathematician giving a lecture on the blackboard with a cup of coffee on the left hand. And then you will see, you know, immediately ChatGPT offering you such an image, okay? So for instance, Duvan was kind enough to send me for my birthday a picture made with ChatGPT in which he gave instructions. It was greatly done, by the way. I don't know how Duvan did it, what the query he introduced in ChatGPT was, but he did very successfully a picture, you know, of a mathematician working in this area, and then ChatGPT did the rest. You know, put the art. So on one hand, algebra, you build this in a discrete manner, but on the other hand, nonlinearity, as indicated here on the left. And the simplest nonlinear function that is, and one of the most efficient ones that is used in machine learning is the so-called rectified linear unit, which is 0 to the left and then linear to the right. You might say, well, this is a very elementary function, indeed, but it has also some very nice properties, like it is Lipschitz. So it's very nice for all kind of stability analysis. You can control the Lipschitz constant. So if you are solving all these with it, you will see the Gromval lemma. Otherwise, you can simply, you know, using the Taylor expansion to first order, you can simply compare the output of the function, knowing that the gradient is less than 1 out of the distance from inputs. Okay, so linear algebra, a network like here, where you have plenty of nodes, many possible connections, just a graph that you can represent on a big matrix together with nonlinear, and then let parameters in every neural network be free. So we use basically 3 parameters. I will explain their role later, A, W, and B. So let A, W, and B, 3 parameters, be free in each of the nodes of the network, and then using the potential that this nonlinear function allows, let's see whether I can find parameter values so that the loss on the left, which means, whether or not I am able to guarantee that this function on the data set I have is taking the correct number of values. I mean, the labels, the values I am given. So can I at least anticipate that these parameters A, W, and B that I will activate on every neuron are able to at least learn that this individual person is drinking 1 coffee per day, and that this other one, by the contrary, is drinking plenty more because he or she is a mathematician. And once I have this function, I can use it to generalize. Generalize being very close to generative, right? The same G, generalize or generative. So I learn on the data set I have, but not only I learn on the data set I have to make sure I have learned. It's like when we prepare ourselves for an exam. We don't prepare ourselves for an exam to make sure that we have learned everything is written in the book. Actually, we learn everything is written in the book to be able to solve the exercises that are not on the book, okay? So this is when we can really show we have learned, the day we can solve exercises that are not on the book. The same here, okay? Very good. Now, this works, and this is what has been done in particular in ChatGPT. I recommend you to have a look to these videos in the channel 3 Blue 1 Brown, when they explain very well how all this, the architecture of ChatGPT works, right? But when you watch one of these videos, you will see one of the first things you learn is that the number of nodes in this graph, right? So the sizes of the matrices we are considering in this process is of the order of 175 billion. So this algebraic nonlinear monster, which is finite dimensional and that has been built in order to be able to learn everything that has been published before, to be able to provide you with summaries or with maybe even generative text of a given topic, like for instance, the uncertainty inequality, right? The principle of uncertainty, the uncertainty principle. This model contains 175 billion parameters. So we are dealing with the course of dimensionality. We are in very high dimension, and this is why high dimensional analysis is extremely important. It's true, we can always say that we are in an Euclidean space of dimension D, but D is not 1, 2, or 3, as in classical applications of mechanics, but is 175 billion. And this number is really huge. And on the other hand, because we have to train these parameters, optimize these parameters by minimizing a loss function that is gathering like in a least square process, right? So we could always claim that Gauss, when developing least square, was the one who initiated artificial intelligence, and that will be true in some sense. So when solving this magnificent giant optimization problem to train to compute the best possible parameters, because of the presence of this very relevant nonlinearity ReLU, right? Because of the presence of the nonlinearity, the optimization process is non-convex, and therefore you are also dealing with the devil of non-convexity, which of course is very harsh when dealing with minimization problems, okay? Despite of this, all this works. And there are some classical results in analysis, in particular in approximation theory, nonlinear approximation theory. This one, for instance, by Sivenko, published in '89 in a control journal. Surprisingly, this is published in a control journal. So I'm not the first one to claim that there is a link between artificial intelligence and control, right? That claims this class of functions is dense. So what is this class of functions? These are not the polynomials as in Stone-Weierstrass. These are not Fourier series. These are series, of course, in which you need indeed, you need to take, more and more terms, capital N, when you want density to be achieved, right? You have some weights, alpha j, of course, that you have also to employ in order to amplify properly each of the ingredients of this series. But then there is a nonlinear function sigma that in the context of neural networks is called the activation function, because somehow it is telling you how much you are activating each of these cells, these neurons of this large network I was drawing before. And then there are two parameters inside, y, which is an scaling parameter that is dilating or compressing the x variable, and theta, which is a shift, is a drift, that is translating the center of gravity of this activation function. Well, what Sivenko said is, listen, this ansatz is dense as soon as the activation function is something like this. He called it sigmoid here to the right, in which you see this transition, this front, evolving from 0 to 1. Actually, when you look to the ancestors of this celebrated result by Sivenko, you see that Norbert Wiener, back in 32, as indicated here down on this slide, so this one here, he was proving something very similar. This is the Tauberian theorem by Wiener, but using the Gaussian as activation function. And little by little, it took 57 years to Sivenko to realize that he could do the same as Wiener did with the Gaussian by using the step function here, the activation function as the sigmoid here. But there was a step further that it was needed in order to guarantee the Tauberian theorem, the density that Wiener claimed for the Gaussians. Wiener, in order to prove the density, he simply used the hypothesis that the activation function should have a non-vanishing Fourier transform. And therefore, the Gaussian is a very good candidate. Now, if you take this kind of step function, of course, the Fourier transform will oscillate. So you cannot apply Wiener's theorem to guarantee that, his result extends from Gaussians to these kind of heavy-side, one-sided functions. But the point that Sivenko did was to observe, listen, but Wiener didn't think on using this scaling parameter. The ansatz of Wiener, the y here was frozen. He was just taking one unique, basis functions like the Gaussian with a given variance, but frozen. And he was just considering whether the density could be generated by translating and weighting the basis function sigma with theta and with alpha. And it is for that reason that Wiener needed the Fourier transform of the basis function to be non-zero everywhere. But what the key remark by Sivenko was, if you allow this scaling parameter, then you can enlarge the class of functions of Wiener, right? In order to, for instance, allow this one and later this ReLU. So why this nonlinearity is so important in these neural network constructions, these graph constructions? Why don't we use a purely linear algebraic model? Well, there is a very clear reason. The first thing you need to do if you want to build a mathematical model that is able to learn from data is to be able to distinguish left and right. If you are, for instance, ordering data, the first thing you need to be able to do is to distinguish colors or distinguish shapes, right? And then this needs precisely to be able to cut a space into two pieces. And the simplest function that is able to do that, probably you will tell me, well, is not the ReLU, is the Heaviside function, 0 on one side and 1 to the other, and you are right. But, the Heaviside function is not continuous, it's not ellipses. If you think on the, the ellipsis replacement of the simplest function that can discriminate left and right, then you think on the ReLU. And this is little by little how, from Tauberian theorem of Wiener to Siebenko, we go to the point where probably nowadays ReLU is the most used nonlinear function for machine learning. Okay, so now note that the same Wiener that in 32 in the Annals of Mathematics was published in this 100 pages paper, probably his PhD thesis, I don't know. He was the one who in 48 wrote the book in cybernetics, and he said that cybernetics was the science of communication and control in animals and machines, a definition that is so valid for control as it is for machine learning and artificial intelligence, right? And somehow it shows that these fields are really, if not brothers, at least twins, okay? And then we can see in a number of applications that indeed, not only when you develop the mathematical computational aspects of solving problems in control theory and in machine learning, the tools are very similar, but in fact, very often in practice, even when you simulate the results in a graphical manner, you see videos that look very much alike. The video on the left is a classical control application where dogs are herding sheep, while on the right, I am classifying particles according to their label, the label being on the right, yellow, green, and purple, using a deep neural network. And you see more or less the same even graphical representation, which is another manifestation of the fact that the two fields and the outputs that the two fields produce are very, very closely related. Okay, so now, as I said before, this is general idea, but there are many different architectures you can consider for these artificial neural network constructions, which is basically a graph plus a nonlinearity. You can change the graph, you can change the nonlinearity. You have different applications, and therefore you will see that there is a lot that has been done in image processing, in neurosciences, in biomedicine, in different applications, developing very, very smart, computer science tools based on these ideas, and also very deep mathematics that have been developed in order to explain the performance of these methods and also to better tune these methods. One of the fields being, of course, Fourier analysis and wavelets, okay? But here, because we are more used to deal with dynamical systems, we adopt a slightly different perspective. So today I will simply talk about the first problem, why this works, right? So, and I will do it in a very elementary manner, but trying also to convince you that this is a topic that deserves a lot of attention from the community of mathematicians, and in particular from the community of mathematical analysts that are mainly represented in this ICMAM conference. So a way in which you are an expert in PDEs or you are an expert in dynamical systems or in control, you will feel comfortable working with machine learning is by considering this ordinary differential equation here. Let me call it neural ordinary differential equation. So the only difference of this ODE with respect to other ODEs is that the nonlinearity sigma here is the ReLU, the one I said before. Very nice, because it's Lipschitz, so the ODE is well posed. The space dimension in which this ODE is evolving will be probably high, because I'm dealing with data. Imagine I'm dealing with images, and then images, the dimension of an image is commensurate to the number of pixels. So you have a very high resolution image. This means immediately you are working in a huge dimensional Euclidean space. And then we have three parameters precisely the same as those appearing in the ansatz of Siebenko, and one more than in the ansatz of the Tauberian theorem of Wiener. We have three parameters. One is the drift, the other one is the scaling B, drift B, scaling A, and intensity W, okay? Now, because I'm adopting the point of view of dynamic control theory that was developed, as you know, in the classical times to deal with problems like sending a rocket from Earth to Moon. So this is clearly a control problem. I am at Earth. I have to get to the Moon, and I need to, gear the engine so that it lands really in the Moon, and not everywhere in the Moon, but precisely on the expected location to guarantee a safe landing and also a return if possible, right? So I have control parameters depending on time. And you see why this is called artificial intelligence, or why this model is called artificial or is called synthetic, is because the model is not inspired in physics. It's just a model I have built, and this is purely arbitrary, but I like it because it's easy to understand, in particular because the nonlinearity is global ellipses, and it works. And this is why it's a satisfactory model. Being artificial, it does the job. And what is the job it does? It does the job of classifying, data. And in particular, so the job that this ODE will do will be to take all these possible initial data here as initial data of your Cauchy problem and be able to distinguish that some of the particles are red and some other particles are blue, and that therefore they have to go to different destinations, different baskets, different regions in order to be, discriminated, separated, right? As I have shown in the previous video. So what is the link of this model with the Sibenko model? Well, the idea is very simple. If you discretize this model in time, you will get into this so-called residual neural network, in which step by step you add one more neuron, one neuron per layer, right? One neuron per step. And this is just a way of organizing our workload on time in a discrete manner compared to the static ansatz of Sibenko. Okay, and precisely, if you do that properly, you see that it works, right? So this is the video that I have shown you before, in which you see that a proper choice of the parameters W, A, and B is able to guarantee that data are properly classified. So let me explain you how it works, and then with this I will try to close the session indicating some possible directions of future work. Why does it work? Well, the theorem here published in Science Review last year says, yes, we can. Meaning that if you give me data in a space dimension greater 2 or greater than 2, not in 1, because in 1, you cannot organize data in 1 dimension. When you start moving them, reordering them, they will collide. You need room, and room appears as soon as you are in dimension 2 or higher. You give me n data, you tell me that this n data, regardless how big n is, how big the dimension d is, how many classes you have according to the different colors, right? So in the simulation, there were 3, yellow, green, and purple, but there can be as many categories as you wish. I can always take the data and bring them all together through the resolution of this Cauchy problem, in which the parameters, the controls, have been defined in such a way that all initial data evolve along the same dynamical system and get to the corresponding destination according to the label. This is a giant simultaneous or ensemble control property that you can only achieve, as I will explain now, because of the presence of the ReLU. The non-linearity in the model is essential. So if you try to do machine learning with linear theory, you will never get it. This ReLU, able to discriminate left and right, plays an essential role in all I'm saying. Of course, there are links with many other disciplines, in particular with the discipline of optimal transport, Monge Kantorovich. A very close link can be seen through the fact that, as you know, ordinary differential equations are the characteristics of transport equations. And when you read what I am saying, what I am actually telling you in the context of transport equations is that I can find vector fields which have this very neural structure. They are just, choosing properly the coefficients W, A, and B on this shape, which is particularly simple, the ReLU. I can find these kind of neural vector fields that are able to transport mass. Why? Because every item is brought to the corresponding basket, so I can bring any atomic measure to any other atomic configuration you give me. So what is the proof? The proof we did is very much based on the Rubik cube principle. So it's an iterative proof. Actually, we do it by induction. The same you do in the Rubik cube. I mean, you don't need to be an expert of the Rubik cube to understand our proof. So we know, as we have shown here on the left and on the right, that the Rubik cube, we solve it in an iterative manner. In each step, we freeze part of the Rubik cube and we make the other part rotate in a strategic direction. And by concatenating these actions, we are able to bring the Rubik cube from any disorder configuration to this one, which is homogeneous, which is a good solution. Why? Because every microphase, according to its color, is in a good coherent phase. And in order to do just one motion, the only thing you have to realize is that at any time with the coefficient A and A and B, the only thing we are choosing is a hyperplane in space, as indicated here, a cutting hyperplane that tells us, listen, if you are to one side, A dot x plus B is negative, and therefore sigma is 0, and therefore the right-hand side is 0, and this particle is frozen. So you see to which point you are generating an artificial dynamical system. It's a synthetic one, it's a virtual one. We don't know of dynamical systems in which, the cloud is moving and then suddenly half of the space is frozen and the other one continues evolution. While if you are on the active part, where A dot x plus B is positive, then sigma is the identity. This is simply a linear ODE, and therefore the active part evolves according to this linear ODE in an exponential manner, following the direction of the wind that W determines. That can be an arbitrary direction in space. And if you do that, you immediately realize that you can indeed classify, like in this exercise, one badly ordered particle, but you also see that by induction, right, this can be iterated in order to be able to show this property of universal classification of neural differential equations. So in this exercise, you see we have 3 blue particles, 3 red, 3 green. 2 blue are well placed in the blue basket, 3 green are well placed in the green basket, 3 red are well placed in the red basket, but 1 blue is misplaced. We have to bring this blue to the blue area, but without undoing the good ordering of the other. My claim is that just by using hyperplanes that are horizontal or vertical, right, you can do that in 4 steps, as indicated in the video. Left frozen, right goes up. Down frozen, up goes left. Up frozen, down goes left. And finally, left frozen, right goes up. And you see that we have achieved a configuration in which the blues are on the blue area, the green in the green, and red in the red. So what is left? Well, plenty is left. So for instance, this drawing is in 2D, but what is the optimal configuration in high space dimensions, right? What about other architectures? I have just here deal with the problem of the neural differential equations, but what about more complicated architectures like the transformers in ChatGPT, which are much more complex? Can we explain with similar ideas their performance? But what is the minimal number of parameters we need, right? So ChatGPT uses 175 billion parameters. It's true, it's a lot, but the information outside is even much bigger, right? So in practice, we are using many, fewer parameters than actually the cardinal of the data set we are representing. How can we explain this expressivity or the generalization capacity. All these needs of quantitative analysis, as I said, combining all the tools we know from Fourier analysis, from PDEs, from numerical analysis, from control theory, and it's a field that I invite you to join. I think is really fascinating, and there is plenty of room in the coming years. Thank you for your attention.
Okay, Professor Suazua, thank you very much for this very inspiring talk. Especially here in Javeriana, we have several young researchers that probably will accept your invitation to join this amazing idea. So now we are open for questions. Are there any questions for Professor Suazua? Maybe here you can make questions in Spanish, you can translate. Don't hesitate to make your question in Spanish. Santiago?
Sí, yo creo.
Okay, maybe Santiago, ¿eh?
Translate.
Incluso puedes hacer la pregunta en español que el profesor Suazua.
Muy buenos días, profesor.
Buenos días, buenos días. Puedes preguntar en español, sí.
Vale, estoy fascinado, digamos, de este tema. Y de pronto, como lo mencionaba, no sé si hay algunos avances que se hayan hecho, digamos, considerando ya dimensiones altas, como lo acabo de decir. De pronto, ¿hay alguna línea de investigación activa en ese sentido?
Sí, es una excelente pregunta. O sea, si realmente no he entrado en eso, pero si tú aplicaras la demostración que yo he comentado aquí y fueras clasificando los puntos uno a uno, como he hecho en este ejemplo, imagínate que tienes 1.000.000 de puntos y que la mayoría de ellos están desordenados, pues sí, el algoritmo funciona. Puedes demostrar que la red neuronal en dimensión 2 o superior es capaz de recolocar todos los puntos en su sitio con un número finito de movimientos. Pero claro, si tienes que llevar los puntos uno a uno y cada uno te lleva 4 pasos, pues tendrías 1.000.000 de puntos, 4 millones de pasos, ¿no? Entonces, la primera pregunta que aparece es ¿por qué se da ese fenómeno de condensación? ¿Por qué tiene que ver también con el sparse sampling, ¿no? Con la, ¿cómo le llaman? Sí, eso, la esparsidad, no sé cómo se diría en español, ¿no? El hecho de que necesitas muchos menos parámetros de los necesarios, ¿no? Nos acordamos de Johnson Lindstrauss, ¿no? Que te dice que en realidad en grandes dimensiones de espacio los datos tienen tendencia a concentrarse en variedades de menor dimensión. Por supuesto que eso es así y posiblemente en ese sentido el resultado más sorprendente que yo he visto es precisamente un alumno de doctorado de nuestro grupo, Antonio Álvarez, que demuestra que si la dimensión es muy grande, en particular si la dimensión D es mayor que el número de partículas que tienes que clasificar, no necesitas hacer zigzags. En una sola dirección del espacio, el sistema autónomo te va a llevar a buen puerto. Entonces, hay muchísimo margen. También tiene mucho que ver con la probabilidad y la combinatoria para entender cómo el número de partículas, por un lado, que tú tienes que clasificar y por otra parte, el espacio en el que te estás moviendo, la dimensión del espacio, cómo juegan entre ellos para permitirte clasificar los datos, representar los datos en definitiva, porque cuando los clasificamos los estamos representando, estamos aprendiendo, ¿no? Cuántos parámetros eso necesita. Y eso evidentemente es esencial, pues lo mismo que lo es en el análisis numérico clásico, donde te van a decir, mira, yo tengo que calcular esta integral, ¿no? El clásico problema de la cuadratura, y tú, bueno, vas a decir, bueno, voy a sustituir esta integral por una fórmula de cuadratura, pues la más sencilla sería la de Riemann, ¿verdad? y entonces yo te voy a decir, bueno, la integral exacta ya sé que no la vas a poder calcular, ¿verdad? Salvo que sea una de esas que preparamos en nuestros exámenes para que el alumno pueda calcular explícitamente la primitiva. Las integrales no se calculan exactamente, pero te voy a decir, ¿puedes decirme, por favor, una aproximación con un error menor que epsilon? Y te voy a decir, y dime cuántos datos has utilizado para samplear la función, ¿verdad? Lo mismo que queremos optimizar ese proceso, aquí se plantea la misma cuestión, ¿vale? Ya sabemos que se puede hacer, pero ¿cómo lo puedes hacer de manera óptima, ¿verdad? Y precisamente lo segundo, que es extremadamente interesante y que ha sido también objeto de muchos análisis y donde en particular el análisis de Fourier es extremadamente interesante porque demuestra que el ordenador aprende de manera multiescala, aprendiendo primero las más bajas frecuencias de la función de la cual se han extraído los datos para después ir aumentando en frecuencia poco a poco, lo mismo que el ojo humano ve, ¿verdad? Porque si nosotros miramos una imagen, si yo miro la pared, yo lo primero que veo es una pared blanca. Y tal vez en una primera mirada no me doy cuenta bueno, que en realidad no es blanca, sino que es gris clara. Y tal vez tengo que hacer una nueva mirada para darme cuenta que la superficie no es lisa, ¿no? Sino que es rugosa, que tiene un gotelet. Y tal vez tengo que mirar de nuevo un poquito más, todavía más a fondo, para darme cuenta que aunque parece que la pared está impecable, hay una grieta. Nosotros también vemos de manera multiescala, ¿verdad? Desde lo más grosero, lo más baja frecuencia hasta lo más alta frecuencia, hasta donde llega nuestra capacidad de ver, ¿no? Entonces, el análisis de Fourier también permite aportar en ese sentido, ¿no? El trabajo de Antonio Álvarez está basado en utilizar el clustering, porque claro, fíjate, en este ejercicio que yo os he mostrado, imagínate que en lugar de haber aquí solamente una partícula azul mal colocada, imagínate que hubiera 3 o 4 en un cogollo alrededor. Bueno, el mismo algoritmo hubiera bastado. No tendría por qué mover cada azul uno a uno. Hubiera cogido un puñado de azules y en esos 4 movimientos los hubiera llevado a su sitio, ¿no? Lo mismo que si me pides ordenar las tizas, pues yo el puñado de las amarillas la voy a llevar a una caja, el puñado de las verdes a otra, el puñado de las blancas a otra. No voy a llevarlas uno a uno, ¿verdad? El clustering de los datos permite rebajar la complejidad, ¿no? Y todo eso es extremadamente fascinante y, como te digo, aunque se ha estudiado en algunas arquitecturas fundamentales de redes de neuronas, todavía queda mucho trabajo para hacer para explicar pues, el increíble éxito, por ejemplo, de herramientas como ChatGPT, que aunque parezca mentira, están haciendo lo que os he contado, eso sí, basado en una arquitectura de redes neuronales muy inteligentemente construida y con muchísimos parámetros, ¿no? Y entrenada con muchos datos y con mucha inteligencia computacional y también recursos computacionales y energía, claro, dinero.
Muchas gracias. Okay.
De nada.
I think we have another question from the room. Si quieres, preséntate.
Espera.
Sí.
Hola, buenas. Primero que todo, no, muy chévere. Me pareció muy interesante todo el tema de verlo desde un punto de vista matemático. Está bien interesante. Yo tenía una pregunta respecto a los algoritmos. Pues yo he visto que, por ejemplo, existen varios tipos de algoritmos al momento de hacer este tipo de problemas. Por ejemplo, el algoritmo que mostró que era pues, como similar al cubo de Rubik. Entonces mi pregunta va enfocada de si de pronto, digamos, al generar estos algoritmos, se hace como un estudio en términos de complejidad computacional para saber la eficiencia a medida que avanzan las dimensiones. O sea, por ejemplo, cuando uno hace un algoritmo que uno estudia, si es como, por ejemplo, n logaritmo de n o n cuadrado, por ejemplo, entonces si se sabe qué algoritmo es más eficiente y se hace este tipo de estudios al momento para saber, pues, a medida que se trabajan con más parámetros, cuál es más complejo y tal.
Hombre, esa es una cuestión fundamental, ¿eh? Gracias por la pregunta. De hecho, antes hemos mencionado, ¿no? The Course of Dimensionality, ¿verdad? Que lo decía aquí, ¿verdad? Seguro que ya lo sabéis, ¿no? Pues el The Course of Dimensionality, el diablo de la dimensión, o sea, ¿qué ocurre? Eh, yo me acuerdo que era yo profesor en la Autónoma y iba a dirigir una tesis de máster a un alumno, a Miguel, un excelente alumno. Y nada, queríamos hacer algo computacional y nos interesaba, era un tema de diseño óptimo y tal, y no teníamos una idea clara de cuál era la respuesta analítica. Y entonces yo le dije a Miguel, mira, muy fácil, vamos a hacerlo numéricamente porque tenemos aquí el solver elementos finitos. Y entonces era un problema como este, aunque en aquel momento no tenía nada que ver con redes neuronales, era una placa, ¿verdad?, en la que teníamos que decidir la configuración del dominio. Era un problema de diseño de formas, extraer el dominio interior a una placa que tuviera un rendimiento óptimo con respecto al laplaciano. Entonces le dije, mira, muy fácil, vamos a hacer un mallado en diferencias finitas. Entonces vamos a coger un número de nodos, ¿no? Pues n aquí, n cuadrado en total. Y ahora vamos a decir que el dominio es simplemente hacer una elección de los nodos, ¿no? Entonces, si eliges este y estos de aquí, pues te va a quedar un dominio así y estos van a quedar fuera. Entonces le dije, muy fácil, vamos a calcular el laplaciano en cada uno de los dominios posibles y luego ya, pues ya veremos a ver cuál es el que parece dar una respuesta óptima. Eso nos va a orientar un poco al tipo de configuración que buscamos, ¿no? Y al de una semana vuelve Miguel y me dice, joder, Enrique, pues aquí estoy y todavía mi ordenador no ha acabado. Y le digo, ¿cómo es que no ha acabado? Vamos a comprobarlo. Y claro, nos dimos cuenta enseguida de por qué. Porque claro, cuando tú coges en un cuadrado en el omega 0,1 por 0,1 del plano, coges n divisiones en x y n divisiones en la variable y n empieza a ser ya un poco grande, digamos 10, ¿no? 10 y 10. Tienes 100 nodos ya en el interior y para cada uno de los nodos puedes elegir si está dentro de tu dominio o no está dentro de tu dominio. El número de dominios que tienes que verificar, aunque solo sea para resolver el laplaciano, es del orden de 2 a la 100. Y ese es un número, como todos sabemos, muy grande. Eso es lo que precisamente Bellman se dio cuenta en el contexto de la teoría del control. Él dijo, eso era los años 60, ya Pontryagin había hecho su principio del máximo para resolver problemas de control, luego vino Bellman con su principio de la programación dinámica y dijo, mira, no es tan difícil. Para encontrar el mejor camino, lo que tienes que hacer es empezar desde el final y siempre dar pasos de modo que cada arco final sea el más corto posible. Teóricamente se puede hacer, pero ¿qué es lo que ocurre? Que cuando subes en dimensión el número de caminos es tan grande, que eso es imposible de verificar. Por eso, todas las técnicas de entrenamiento de Machine Learning no son absolutamente exhaustivas. Utilizan extremadamente el stochastic gradient, el gradiente estocástico, porque mucho de lo que hacemos necesariamente se tiene que apoyar en el azar, en la capacidad de repetir, en el azar y en la confianza de que sampleando muchos posibles escenarios, al final encuentras uno que funciona bastante bien, ¿verdad? Pero como bien dices, la complejidad algorítmica, cómo esa complejidad aumenta con la dimensión, con el dataset, qué nivel de fiabilidad eso tiene a nivel de generalización, que es la gran pregunta. Como he dicho, a uno le gustaría crear un modelo de redes de neuronas, no solamente que se pueda aprender a partir de las radiografías de los enfermos del histórico del hospital quién estaba sano y quién estaba enfermo, si lo que queremos es que luego esa máquina pueda ayudar al doctor a partir de la imagen a decidir si ese es un caso de riesgo o es un caso que puede ignorar porque ese paciente está sano. Queremos generalizar. Entonces, ese error de generalización, cuantificarlo y ligarlo, como tú has dicho, a ese otro coste que sería el coste algorítmico de entrenar, de calcular esos parámetros, son problemas fascinantes. Y claro que hay mucha literatura sobre eso, pero sin duda todavía queda muchísimo por hacer, ¿no? Es sin duda pues toda la teoría de la información, complejidad. Son temas también que muchas veces empiezan a penetrar en otros campos, no solamente son exclusivos de los matemáticos, por supuesto, ¿no? ¿Vale? El computer science, esto es el machine learning, la inteligencia artificial, en gran medida se ha hecho por científicos que no eran matemáticos, o si lo eran en su origen, trabajando en contextos muy out of the box, sin pensar como hacemos los matemáticos tradicionales, que no somos capaces de dar un paso si el anterior no está absolutamente, ¿no?, validado, ¿verdad? Esto ha sido todo muy heurístico, pero has visto hasta dónde nos ha llevado, ¿no? El premio Nobel de Física, repito, este año está dedicado a dos personas que han contribuido precisamente con una formación matemática, un pensamiento matemático, pero sin estar atados por el rigor matemático, mucha heurística, mucha intuición y imaginación también, y sobre todo una mentalidad muy orientada a resolver problemas, ¿no? No a demostrar teoremas, sino a resolver problemas.
No. Vale, muchísimas gracias.
De nada.
Okay, hay entusiasmo con preguntas a la charla del profesor Suazua, Juan Pablo López, de la Universidad del Valle.
Bueno, primero gracias por la charla. Yo tenía como una curiosidad, y es que cuando vi el problema de clasificar, me pregunté, bueno, si uno lo podría considerar en el caso inicial en donde están desordenadas las bolitas de colores, si uno podría considerarlo como una densidad de probabilidad inicialmente, en donde pues tengo una probabilidad de encontrar en el lado azul tantas pelotitas azules, en el lado rojo tantas pelotitas azules y en el lado verde tantas pelotitas azules. Y la idea es pues partir de esa, o sea, yo lo vi así, ¿no? Como partir de esa primera distribución de probabilidad hacia una en donde la probabilidad de encontrar un azul en una roja sea cero, un azul en el lado verde sea cero. Y pues ver esto como este problema como si fuera un problema de transporte de distribuciones, ¿no? No sé si de pronto se ha considerado, incluso con...
Tienes toda la razón. El planteamiento que yo he hecho así un poco determinista, ¿no?, de llevar bolitas de un lugar a otro y tal, es posiblemente, bueno, pues eso, está muy condicionado por la manera de pensar un poco determinista, como, bueno, pues como hacemos muchas veces en análisis, ¿no? Pero, por ejemplo, en esta página ya, fíjate, aquí se evocan también un par de cosas más que me gustaría mencionar. Fíjate, una de las primeras cosas que los informáticos que se dedicaron a construir estos engendros, ¿no?, como ChatGPT, tuvieron que resolver es la siguiente. A ver, tú tienes el Quijote, por ejemplo, ¿verdad? Tienes el Quijote, vale. Ahí hay un montón de palabras. Pero, ¿dónde están los labels? Porque cuando yo te he dado bolitas había colores, ¿verdad? Y todos distinguimos los colores, el azul, el verde y el rojo, vale, perfecto. Pero yo te doy el Quijote. ¿Y dónde están los labels? Tienes un montón de palabras, ¿dónde están los labels? Entonces, enseguida ellos dijeron, vamos a pasar del supervised learning, que es el paradigma que yo os he contado, donde tú tienes fotos de miembros de tu familia, por ejemplo. Supervised learning es lo que hace el ordenador. Abres tu foto folder. Yo cuando lo abro es un desastre, hay 10.000 fotos, la mayoría seguramente no valen para nada, pero no me voy a preocupar en ir borrando una por una. Pero sí que me gusta, por ejemplo, las fotos de las personas más queridas, más importantes para mí, tenerlas más o menos en un folder, ¿no? Afortunadamente, eso te lo hace automáticamente el ordenador. Tú le haces clic a una foto y dices, mira, esta es la foto de mi hermano. Le dices, es de mi hermano y se llama Pedro. Y le das al botón y el ordenador va a tardar un rato y al de un rato te va a abrir el folder Pedro y vas a decir, ahí va, si hay 314 fotos, el ordenador ha sido capaz de encontrar esa persona y con un margen de error pequeño, porque puede equivocarse obviamente, pero con un margen de error pequeño, plum, te coloca en el folder de Pedro, ¿no? Claro, si le pides que haga eso con dos gemelos, te vas a dar cuenta que se empieza a confundir. ¿Por qué? Porque está basado en ese principio de guess the next word, ¿vale? O sea que lo que hicieron para pasar del paradigma del puramente supervisado, en el que tú le has dado un label a cada palabra, intentas aprender a partir de textos, la manera en que de un texto consiguieron sacar los features, los datos, los items y su corresponding label, su etiqueta, fue decir, cada conjunto de n palabras consecutivas tiene un label que es la n+1. Entonces, fíjate qué idea tan ingeniosa y tan elemental, pero ahora de repente tú te coges el Quijote, tienes, ¿no? Millones de palabras hay escritas, ¿verdad? Y coges cadenas de n de ellas, siempre puedes a una cadena de n de ellas asociarle un label que es la n+1ésima. Eso es lo que se llama el self-supervised learning. Tú puedes aprender, es como si tú miraras tu histórica de comportamiento para ver que efectivamente coges secuencias de tu vida de n minutos o n horas y empiezas a ver un pattern que te permite ir aprendiendo qué es lo que más probablemente ocurra después. Y como tú bien dices, cuando se entrenan esos modelos no hay determinismo. Por eso, en ChatGPT también tú le haces una pregunta hoy y se le haces mañana y la respuesta no es idéntica. ¿Vale? Porque incluso hay un área de investigación también que no he comentado, que es lo que se le llama el prompt engineering. Es en ChatGPT, en estos Large Language Models en general, cómo haces la pregunta importa. Tú puedes preguntar lo mismo, pero depende de cómo tú formules esa pregunta, la respuesta va a ser distinta. ¿Por qué? Porque al fin y al cabo, yo os he mostrado esta Neural Differential Equation. ChatGPT es un monstruo mucho más complejo, ¿verdad? Es un alien. Pero no deja de comportarse un poco parecido, de modo que cuando tú haces una pregunta, lo que estás poniendo es un dato inicial en ¿no? En tu problema de Cauchy. Y la respuesta es la salida al cabo de tiempo t. Entonces, claro, pasa, ¿no? Como en el sistema de Lorentz, ¿verdad? Que pequeños cambios, el efecto mariposa, pequeños cambios en cómo tú haces la pregunta, te pueden dar lugar a diferentes respuestas, ¿no? Pero, por ejemplo, si veis el primer vídeo de esta serie que os recomendaba, de Three Blue, One Brown, veréis que el primer vídeo os explica cómo construir una red de neuronas que resuelva un problema bastante sencillo, pero a la vez ya suficientemente sofisticado, de image processing o de pattern recognition, que consiste en simplemente, a partir de imágenes de dígitos escritos por una persona, que el ordenador, cuando luego tú le das un nuevo garabato, sea capaz de decir esto es un 7, esto es un 8 o esto es un 9. Pero en realidad, como tú bien has explicado, la respuesta que en realidad encuentra el ordenador no es una respuesta determinista, es una respuesta probabilística. Lo que realmente, a través de cadenas de Markov enriquecidas, porque antes cuando hablaba del álgebra y de las redes, no lo he dicho, la palabra clave ahí es cadena de Markov iterativa en el tiempo, junto con el efecto no lineal discriminatorio de la ReLU que antes he mencionado. Lo que el ordenador hace es, va aprendiendo de los dígitos escritos por humanos que ya están clasificados bien como 7, como 8, como 9, etcétera, y lo que el ordenador hace cuando yo le pinto un nuevo garabato, ¿no? Como, no sé si lo puedo hacer ahora, pinto un nuevo garabato que es este, pues el ordenador lo que hace es, en los diferentes dígitos que van desde el 0 hasta el 9, asigna una salida que va a ser un vector de componentes positivas de sumatorio 1, va a ser una distribución de probabilidad en la que vamos a ver que no me va a salir una delta de Dirac, nunca. Lo que me va a salir genéricamente es un vector con entradas positivas, con 10 componentes, ¿no? Positivas todas ellas, cuya suma es 1, porque es una probabilidad discreta, pero lo que va a ocurrir, porque este 7 es muy claro, ¿vale? Y el ordenador ha sido entrenado adecuadamente, me va a salir un vector en el cual las componentes relativas a, por ejemplo, a la probabilidad de que este número sea un 0 va a ser pequeñísima, ¿vale? La probabilidad de que sea un 3 va a ser también muy pequeña y, sin embargo, la probabilidad de que sea un 7 pues va a ser del orden de 998, ¿vale? Sin embargo, si el número que yo pinto, aunque yo quisiera pintar un 7, lo hiciera, por ejemplo, así, ¿vale? Pues ahora el ordenador va a tener que decidir si eso es un 7 y posiblemente va a dudar entre si es un 7 y si es un 1. Si no me das ninguna información de contexto, hombre, si me dices que estamos jugando al balonmano, ¿verdad? Pues ya sé que es 7. Pero si estamos en un contexto general, tú me enseñas ese número y me dices, Enrique, eso es 1 o un 7, pues le va a pasar lo mismo al ordenador. Entonces el ordenador va a dar un vector, ¿vale? En el cual nuevamente las componentes, por ejemplo, relativas a que esto sea un 0 van a ser muy pequeñas, la relativa a que eso sea un 4 pues también va a ser muy pequeña, pero la del 1 y la del 7 se van a quedar en torno al 0,4 X repartido porque ahí hay una gran incertidumbre, ¿no? Eso es siempre el error de generalización, ¿no? Pero claro, ahí también tenemos que saber qué es lo que le estamos pidiendo a la máquina, ¿no? Le estamos pidiendo a la máquina más allá de lo que realmente es posible decidir, ¿no? Entonces, entre esa figura, yo no le puedo decir a la máquina que me aseguro que eso es un 7 o es un 1, porque no es una pregunta que esté bien planteada. Eso puede ser un 1 y puede ser un 7, y tiene una probabilidad de ser 7 o 1 que depende incluso de dónde es la persona que lo ha escrito, porque un europeo al 7 siempre le pondría el rabito y, sin embargo, pues muchas veces en Estados Unidos y en América no se pone, y esto es lo que aumenta la probabilidad de que este objeto sea un 7. En Europa esto no sería un 7, sería un 1. O sea que es todo muy, muy probabilístico, ¿verdad? Tienes toda la razón. Entonces, es un campo que hereda mucho de las cadenas de Markov y del planteamiento probabilístico, pues que viene eso, de gente como Markov y Kolmogorov, etcétera, que ya en la época pues estaban hablando de problemas pues como dinámica de poblaciones y tal, ¿no? Entonces, claro, en realidad, cuando uno mira lo que es el Machine Learning, pues el Machine Learning es un área, lo habéis visto en ese gap que hay del 32 de Wiener, la época gloriosa, ¿verdad? De Paley, de Littlewood, de Hardy, de Wiener, etcétera, los años 30. De los años 30 de Wiener al teorema que se llama de aproximación universal, que no es más que la densidad de ese ansas de redes neuronales en espacios tipo L1, LP, L2 o funciones continuas, etcétera. Hay un gap ahí de más de 50 años en el cual el campo obviamente está evolucionando, pero está evolucionando lentamente, y la razón de eso es que en todos esos años no había ordenadores capaces de poder experimentar con esas herramientas con agilidad. Fijaros que cuando Sibenko saca su paper en el año 89, para entonces ya el Macintosh, el Apple, era un ordenador de mesa, ¿no? Obviamente eran mucho menos potentes que los que tenemos hoy en día, pero ya formaba parte de lo que era el mobiliario de un laboratorio de matemáticos, por ejemplo, ¿no? Entonces, claro, coinciden las dos cosas, ¿verdad? Y a partir de ahí se da la revolución, claro. Luego viene Google, vienen los datos, viene Internet, viene la capacidad de incorporar cada vez más información, porque está en Internet, la copias y la pegas, ¿no? Te puedes copiar todos los resúmenes de Massinet, por ejemplo. Y entonces luego empezar a, por ejemplo, utilizar los resúmenes de Massinet, por ejemplo, en Massinet, cuando tenemos que poner la clasificación, ¿verdad? Si es 35P18 o 93B27, ¿verdad? La clasificación bueno, podríamos entrenar la máquina a hacerlo, ¿no? Tendríamos que darle muchos resúmenes con muchas clasificaciones ya puestas y el ordenador te daría una propuesta. Pero ojo, que aunque aparentemente te dé una respuesta determinista, porque claro, nosotros cuando vemos una respuesta es la respuesta que nos dan, ¿vale? Y nosotros creemos que esa respuesta está dada, ¿vale? Tras una reflexión que conduce a la certidumbre, pero no es así. La respuesta de ChatGPT es probabilística. Y lo que pasa es que dentro de esa respuesta probabilística te ofrece obviamente la que es más probable, ¿verdad? Pero no hay certeza. Entonces, todo esto, tienes toda la razón, no solamente aparecen problemas de estimar los órdenes o los errores de generalización o la complejidad algorítmica, sino que todo eso hay que hacerlo en un lenguaje además probabilístico, ¿vale? No podemos hablar de generalización en un sentido determinista, sino que hay que hablar de most likely, ¿no? O en probabilidad grande, ¿verdad? Por ejemplo, antes mencionaba el trabajo de nuestro alumno Antonio Álvarez, él demuestra eso, ¿no? Que si la dimensión D es mayor que N, tú puedes controlar la Neural y clasificar datos utilizando coeficientes A, B y W que están congelados, no necesitas ningún switching, es simplemente elegir bien la dirección del viento y el posicionamiento de la ReLU y eso te conduce los datos sorprendentemente a su destino, ¿verdad? Pero si no, pues lo puedes hacer de manera probabilística. Con gran probabilidad lo puedes hacer utilizando un switching, 2 switching, 3 switchings. Sí, la probabilidad es otro de los grandes protagonistas de toda esta teoría, ¿no?
Gracias, profe.
Okay, so thank you very much, Professor Suazua, for joining us. Welcome always to ICMAM Latin America, to our conferences. So now we continue with our scientific program. Then I will pass the chairing duties to Jenny Fragnelli, our organizer from Italy.
So thank you, Duvan, and thank you, Jenny, for your kind
Thanks
invitation.
you, Enrique.
Yeah, thank you for the
Very
opportunity.
nice talk.
Thank you.
So, Elan, you can share your screen, I think. We cannot see you, but we can see your slide. And we cannot hear you. I don't know if there are some problem.
I will put sound.
Okay, now, okay, now it's okay.
Because
can
my
see you
screen is
and-
very small from here. I don't know why, but anyhow.
No, but now we can see you and we can hear you. So nice to see you. Thanks to accept our invitation. So I just works on Hélène. Hélène is a professor at Sorbonne University. She's a worldwide known expert in control theory and set-valued analysis. She got her PhD in 1984 under the supervisions of Oleg and Jean-Pierre Aubin. Just to understand the level of Hélène in her PhD jury, there were also Schwarz, Ekeland, Pierre-Louis Lyons, Rockefeller, Waldschmidt. She's editor of a lot of important journals, for example, SciCon, and editor-in-chief of a Journal of Mathematical Analysis and Applications since 2020. This year, she has been awarded by ICMAM for her contributions to optimal control theory, differential inclusions, and contribution in Wasserstein spaces. She wrote about 150 papers with about 4,000 citations. So for me, it's a pleasure to have Ellen in this workshop. Thanks, Ellen.
So thank you very much, Jenny. So I have 40 minutes starting from now, I guess, yeah?
Yeah.
Yeah, okay, so I have to watch after. Yeah, so thanks for this invitation to the organizers. It's of course a pleasure to present the research work. And today I will speak about control systems on Wasserstein spaces. So Wasserstein spaces are spaces of Borel probability measures. They are not vector spaces. So once you are in, you have to think what should be called, for instance, the derivative, because usually we define derivative using translations of vectors, but here there is no translation at all. And so, and what is the reason to look on the spaces of probability measures? The reason is basically coming from various interests in models in social sciences, for instance, like evacuation model, where you are interested to evacuate as many people as possible, and you do not care who they are really. This number of them is interesting for you. And also when there are systems where there are many, many agents, then also to control such a system may become a quite difficult task because memory will be quickly saturated. And so finally one starts to think maybe we could control rather sets, moving sets. And this is several branches of mathematics, set value analysis in particular, work with sets rather with vectors. But in Wasserstein spaces, there is an extra step that is made to each set one associates its probability measure, each Borel set. So in a way, we are controlling measures. So let me give just two pictures as examples. So this is multi-agent systems in erasing in nature. Of course, in systems like this one could describe dynamic of every individual and then say what will happen in some time, provided you know well the velocities, directions, etc. But you can see this kind of lines as well as a set. So when you know the leader, its direction and speed, when you know length of the line, then you can predict what will happen later on. Same is happening with such as triangular formation of birds, where birds are flying forward. And since their initial conditions are distributed by triangle, this is natural laws, then they just keep keeping the same speed. They will keep this formation of triangles. Of course, there are different also other shapes in the nature where the group of agents is moving and you are not interested by the particular individuals. So in human activities, something very similar is happening, that one is putting kind of controller, a leader, we can say. Here is leader is behind, and this leader was trained to bring ships in the same direction in group. This is another situation. It is French team during Winter Olympics in China. Here, leader is this lady. She's imposing speed. So the initial position are distributed on this letter V, probably victory, and people are just advancing with the same speed. So same kind of situation, of course, arises when there are some military parade or Olympic Games openings. And today I will speak about mathematics that can be done on the spaces of probability measures. It became a very popular topic, in particular in transport equations. In optimal transport, you can find a lot of different books. So my talk basically concerns the control theory adapted to this kind of framework. So I will start by providing a motivating example, and then I will go to Wasserstein spaces, as I will define a metric on them. Then I will introduce differential equations on the spaces, so the metric spaces. So of course, understanding the differential equation is different. That's what we are usually used in the Euclidean or Banach spaces network framework. And then my main result will be concentrated here, state-constrained inclusions or state-constrained differential equation, where not only we would like to solve our differential equations, but we would like also they satisfy some constraints. This is extremely important in applications like, for instance, sustainable development, that you should not consume more resources that there is borderline of consumption. This can arise also in economy, for instance, and also in robotics. A robot is not supposed to go through the walls, so it should respect the obstacles. And so this will be the topic number 4. And then I will briefly discuss how this topic number 4 can be applied to study Hamilton-Jacobi-Bellman equations and optimal control, but again on Wasserstein spaces. So let me start by this motivating example. So we have here a control system, a very simple one in a Euclidean space. So the same control is applied, but initial conditions are different. So it is a group of people moving according to the dynamics, but since they started from different initial conditions, once you put the same control and suppose, for instance, that f is Lipschitz in x, then they will not bump at each other, but the trajectories will be neither the same because it's non-linear system in general. And let us suppose that the objective is to get as close as possible to a set C at time t. So to solve this kind of problems, one formulates a cost, and this cost should be distance between this agents, axis at time t, and the set C. So let us complicate a little bit the framework, say that we would like that the person number 1 arrives closer than others to the set C, or as close as possible in our framework. So the trick would be to put a big weight here in front of the distance. Then, of course, when we are minimizing, if the coefficient is quite big with respect to others, that it's more likely that x1 will be closer to C than others. And so to solve this kind of problems in Euclidean framework or even in Banach spaces framework, one is seeking for tools like necessary and sufficient optimality conditions. And there's also dynamic programming that was mentioned just a moment before. And they all bump in same difficulties. When there are many agents, then this memory is saturated and it is quite impossible to use this theoretical results. Well, one could as well think, instead of moving at each point, one can think about moving sets. Then in this case, somehow you diminish the number of variables because you unify them by sets. And so one can reformulate exactly the same problem by using measures here. So how is this done? So we consider a very same control system. So x0 is now initial condition. And we associate to it a solution operator, which to each initial condition x0 at time 0 associate the final state at time t. Then we impose this probability, we define a probability measure, imposing bigger weight to the person number 1, so-called initial condition at x1. There will be big weight, and for others will be the weight is much smaller. Delta here is the Dirac measure. And then one is defining so-called push forward of this measure mu in the following way. We take this operator and we say that for each Borel subset of RD, the measure of B is the same as measure of inverse image of B. So it is kind of invariance that in this situation, if our agent started at point x10, it will remain all the time as important as it is at the beginning. And then just believe me, but it's easy to justify it, that the same control problem can become a problem of minimization over all controls of this integral, where we integrate with respect to this measure. And so this is giving you ideas that in fact one can imagine much larger number of models that are formulated in this way, associated cost, because you could as well to say not one, but 3 agents are very important, or even a group of agents is very important, and or set of agents, and then it will be all the time the same writing. So this is important in modelization. So let me now go to mathematics that was developed, adapted to this kind of framework. So I will denote in this way the set of all Borel probability measures, and in this set I distinguish those that having finite p momentum. So p is larger than 1, so we define the momentum to power p in this way. And then I will consider this set. This will be the space for me of Wassersteins that I will introduce in a moment together with metric. And these are all measures having finite p momentum. And this notation will be used sometimes to denote measures which are having compact support. That means outside of a compact, measure of the sets is equal to 0. And measures will be acting on continuous functions. So this is, of course, not a Banach space, because RD is not a compact, but one still can introduce metric structure on the set by defining the following metric. And so the distance between 2 functions is defined in this way. And here is just the norm in the Banach space of functions defined on the ball of center 0 and radius k, so it's compact. And this metric is quite nice because it makes from this space a complete separable space. And moreover, this metric is shift invariant, so it is so-called Fréchet spaces. So now the intention of this transparency is to reduce the distance between 2 probability measures, which have finite p momentum. How is it done? So in principle, when we would like to define a distance between 2 points in a Banach space, let's say, you just draw something like or construct interval between 2, and you would say that the length of this interval is the distance. So define the distance between 2 measures. The idea is a bit of similar. One is considering a measure which plays the role of interval here, but it will be defined on the product of 2. And so this measure I will consider almost like an interval, because I will ask from this measure to take on one side of it the value mu, on the other side mu. So let me just explain this notation now. So this appeared already on the previous transparency. So now it is more general. Let us take a Borel map between 2 Euclidean spaces, not of the same dimension. And we define for a measure mu, push forward of mu by this formula. So theta is not even supposed to be invertible here. It is not important. So measure of Borel set B will be measure of inverse match of B by theta. And then let us consider the product of 2 Euclidean spaces and denote by P1 and P2 projections on the first and second variable. And then we consider this element. So we take gamma on this product, probability measure in this product, and I ask that push forward of gamma by the first projection should be equal to mu, and by the second projection should be equal to mu. Such gammas are called transport plans between mu and nu, and one defines them as Wasserstein distance between 2 measures by considering the following equality. So it is p power of the Wasserstein distance is defined as minimum of this quantity, where gamma are all transport plans between mu and nu. What is known is that this minimum is attained, but in general it is not unique. And so all transport plans which are realizing this minimum will be denoted by gamma 0. So they're called optimal transport plans. And this is quite a nice metric because it makes from our set with finite p momentum, a complete separable metric space. So this is nice, but of course it is still not vector space, so you cannot do whatever you like here with measures. And I will show you what is happening now when on the level of measures when you want in a way translate it. So let us consider a set Q in Wasserstein space and a measure in this set Q and define tangent to Q at mu. And this is defined as the set of all functions, which are on one hand p integrable with respect to measure mu, as written here, and they should be also Borel measurable. One cannot take just this only restriction because push forward in all literature is defined only for Borel sets. So to have here push forward of a measure by this expression, one needs psi to be Borel. So if when we push forward a measure mu, it becomes infinitesimally closer to the set Q, then we say that this psi is tangent. And infinitesimally close is understood in the form in the sense of lower limit, not just limit, but lower limit. And this is completely inspired by what we know to do in vector spaces. So when we have, let's say X will be a Banach space, and we take a set K, and the point X and K, then tangents are defined in this way. So this is definition of tangents to any set. So it's not really like notions of differential geometry. One doesn't ask anything from K. And this notion was introduced by Peano in 1870. But then later on, it was rediscovered by many people later on, and so it has various names. So, if you compare this definition, which was written here, they're very similar, but only we don't translate measure. So instead of translation, we're using this push forward mode. And this is one of important notions, by the way, on non-smooth analysis. One has as well to define proximal normals. Again, proximal normals in principle is a notion of differential geometry, but here it is adapted to the framework of Wasserstein space. So let me start by introducing perpendicular. So of course, perpendicular in metric space doesn't have much sense, but by analogy, we could call them still perpendicular. So what is happening here? Let us take two measures in P2. This was done only for P2 and the transport plan between the two measures. And we say that the function gamma bar, which is square integrable with respect to measure mu, is barycentric projection of gamma onto mu if the following equality holds true for every f, which is essentially bounded with respect to measure mu. So what is known that this barycentric projection is unique once you fix gamma, and it exists. So now to define perpendicular, one performs the following. So let us take any nu in P2 space and the subset Q in P2 space, and let us suppose that we can find a projection of nu, which is not necessarily unique, and in general it may not even exist. But let us assume that there exists mu, which realizes the distance between mu and Q. And then let us associate to this mu and mu an optimal transport plan. So there may be many of them. And then with this optimal transport plan, by this result, we know we can associate a barycentric projection alpha bar. Then let us define a function. So it is L2 function between alpha bar, I'm sorry, with function which is just the difference of alpha bar and identity. So this is a definition. And we ask this P to satisfy this equality only mu almost everywhere. So outside, well, places where measure of mu is equal to 0, this peak can be anything. It's not important for computation. And this is called perpendicular. So next transparency will explain why it is called perpendicular, but we just borrowed the language of finite dimensional spaces. So with any perpendicular, one can associate proximal normals by multiplying them by non-negative numbers. And this is a notation of the set of all proximal normals. It's called also proximal normal cone in the non-smooth analysis literature, but which was done mostly for Hilbert kind of spaces. So let me explain why we operate here with the notion of perpendicular. Let us assume that we have a closed subset and y0 is somewhere in RD, and let us project this y0 on the set Q. So there will be many projections. Let us take one of them, x0. So it realizes the distance between y0 and Q. And let us assume this calligraphic set Q, about which I was speaking before, is composed just from direct measures when Q changes in the set. Then, if we define P by setting it equal to y0 minus x0 at x0, and everywhere outside it is anything, but we only care what is happening on the set, one can think that this finally, in the literature, this y0 minus x0 is called perpendicular to the set Q. So here we get a function which is in a way the same that was done here, but in a vector space. So it makes thinking that you deal with something which is perpendicular. That's why language came in. So let me now move to differential equations on the Wasserstein space. So it is, I will call you that it is just a metric space. So to speak about differential equation, one of course needs some machinery. And my differential equation will be like transport equations. It is written here. V here is a function. It's a velocity, which depends on time and on state. But here we don't write it down. And let us fix initial condition. And we say that a curve of mu of measures, so it is absolutely continuous mapping from 0, 1 to the Wasserstein space, solves this differential equation. It's called usually continuity equation, if it is solution in the sense of distributions. That means if for any test function phi, we have the following equality verified. So here we have double integral. One is integrating for fixed t with respect to measure mu of t. And so it's measure which is depending on state, and then integrating with respect to time. Then, of course, this definition may look a bit heavy, like always with test functions, but what is nice here that when you assume that V is Lipschitz with respect to the second variable, just measurable in time, then one can show that one has, in fact, explicit solution to this type of equation, and it will be defined in this way. So here, mu0 is initial condition, and here is push forward operator, but we are pushing forward by solutions of this ordinary differential equation. So in a way, solution is represented by characteristics associated to this equation. So, and of course, this is very helpful when you have this V not depending on measure itself. That means this term is just depending on time on the states in RD, but nothing else. If you start to put that V depends also on measures, then of course one has to do definition again. And let me say that also the literature around this kind of equation developed very much around the cases when V are Borel functions. And there are plenty of theorems here, and they are much more complicated. For instance, you can have a measure which is a curve of measure which is absolutely continuous, and you can show that you can always find a Borel function which will satisfy, for which as this mu satisfies this equation. However, like an ordinary differential equation, when you have V which may be discontinuous, then solutions may be not uniquely defined, and for some V's, solutions may be not defined at all. But when we are coming from control theory, the situation is very much different, because in control, engineers usually prefer to have the following, that you plug in a control, you should get a unique solution. To get unique solution, it's natural to assume that your data are Lipschitz. And so we always assume that they're Lipschitz, and so we have this explicit representation. So if you move toward controlled continuity equations, which also depend, well, dynamic depends on measures, then we say that absolutely continuous curve solves this controlled continuity equation. You here control, so it is Lebesgue measurable function. If whenever we define VTX in this way, then this mu solves this equation. So it is like ordinary differential equation where dynamics are nonlinear. One can go from this kind of considerations also to much more complicated structures, so-called differential inclusions, where you rewrite the same transport equation, but instead of writing equality, you say that it belongs to something, and this something is defined by set-valued map, taking values in continuous functions. So, and here the only difference that now what should be called solution, we say that mu is solution if we can find a measurable selection, Lebesgue measurable selection in this map, in such a way that with this Lebesgue measurable selection, mu solves these equations, which looks like linear. So I will show you theorems, but of course one needs some assumptions. So I don't want to develop it just for a moment. You can look later on these assumptions. These are very much assumptions that you meet usually in ordinary differential equations theory. You assume, for instance, that every velocity in your right-hand side is sublinear in the sense. You assume that every velocity in the right-hand side is Lipschitz with respect to x variable, and Lipschitz constants are uniformly bounded by an integrable function. And then you also assume that the fact that this set-valued map F depends also in a Lipschitz way of measures in the following sense, that it's like in Hausdorff matrix, if you know it. If V, for each V in this set, we can find W in this set, so it is a different measure here, such that supremum distance between these two functions is measured by, estimated by Lipschitz constant times the Wasserstein distance between two measures. So here is just one short example. So if we take a function f, which depends on 4 variables, time, measure, control, and state in RT, and if we assume that f is measurable in T, continuous in U, and with respect to mu x, it is Lipschitz in appropriate matrix, and if we assume also that U is a compact metric space, then we can introduce set-valued map as the set of all functions of this type. So it means that we fix T mu U, and we consider this function as a function of x only. And then this will be, in fact, the Lipschitz function because we assumed this. And then what is important that solutions of differential inclusions with this set-valued map do coincide with solutions to this controlled continuity equation. And this is a very important step in control theory because you can then develop the theory working with sets instead of these long expressions, and then say that anyhow solutions are the same. So to each solution of differential inclusion, I can associate a control such that it will be a solution to control. And with working with differential inclusion may be sometimes simpler. For instance, one can get inspiration from early Cesari work and to prove that in addition F has convex values, then the set of solutions of differential inclusion is compact. And this is very important, of course, because when you have problems of optimality, you have to find the optimal solution. So you need to know that they exist. So to have the set of solutions compact, of course, will guarantee existence of solutions for instance, lava semi-continuous cost. So now I will formulate this viability and invariance theorems. And let me recall just that we say that a set is called proper. So in my case, the set will be a subset in the Wasserstein space if its intersections with closed balls are compact. For instance, if your set Q is composed of measures which have support contained in a common compact set, then this set is proper. So what is viability property? This is the following one. So we consider our differential inclusion, or it could come from control system, and we say that a set Q is viable under the set valued map F if for every initial time and initial condition at time tau, so it's here, it is underlined, we can find a solution, define it on time interval tau 1, starting at mu tau at time tau, such that the solution respects constraints, as written here. And we say that the same set is invariant, even we can say this about every solution, that it will remain in Q. For instance, you may be interested to find only measures which are taking values in a prescribed set, and this can be reformulated as state constraint. So here is this main results that I wanted to show you. One can prove that a set Q, which is proper here, is viable under set valued map if and only if the set of velocities, so these are right-hand sides, so these are continuous functions, intersects the convex hull of tangent to Q and nu, and this should happen for almost every T and for every nu in T. And if one would like to speak about the invariance, then instead of intersection, one just put that it belongs. And then you can, if this happens, then you are guaranteed that all your solutions will respect state constraints. This kind of conditions becoming have also some dual formulations, because these tangents are primal formulations, some dual formulations, if we in P2. So here is this dual formulation. So first of all, I introduce a subset of my tangents, which is composed of Lipschitz functions only. And then polar to this subset is defined as sets of all square integrable functions from Rd to Rd, such that this integral is non-positive for every phi f in the set. Then one can show that proximal normal cone in fact is contained here. And so here is my framework now. I consider F, which is defined on product of these two spaces, two metric spaces, which takes Lipschitz values. And I suppose that all functions that take values in Lipschitz functions which are bounded. So I assume that they are all having Lipschitz constant bounded by some A, and they are also having, they are uniformly bounded on the whole space. And also that they are Lipschitz with respect to the first variable, with respect to measure, in the sense that is written here. Then to say that my viability conditions like this one is verified with convex hull is equivalent to saying that this one is verified, but also equivalent to saying that for every proximal normal, we can write this inequality for any mu and q, or that for any mu and nu, which verifies this projection property, that means nu is projected on q at projection nu, we can find a proximal normal for which this inequality is verified. Let me just recall you that proximal normals are associated to optimal transport plans. So there may be many optimal transport plans between mu and nu, and so each of them may define a different proximal normal. So this is much less restrictive condition than this one because it only exists. This is a very non-trivial theorem mathematically, because to say that a set intersects, this set is, even if it is convex, but to say that it intersects a convex set or to say it intersects a non-convex set, of course, not equivalent in general. But here, what is compensating that what we are asking that this should be verified for every mu, and F is having some regularity properties as well. So this is the last part of my talk. So now I will speak about Hamilton-Jacobi equation. So let me again consider the controlled continuity equation. And I will now restrict my attention to situation where measures, initial conditions are having compact support. Then this result, which is saying that if you take as initial condition a measure whose support is contained in the ball of radius r, then under all my assumptions that imposed here, you can find a unique solution mu associated to each control, but this solution mu will also have compact support for every t. And moreover, we can measure these compact supports, but saying that they are not greater, that they are all contained in the ball of radius r plus rho t. Rho was bound on this function, common bound. So let me show you one optimal control problem that formulated now on Wasserstein spaces. We would like, this is kind of academic problem because it asks to write less writing, so preferable to write in this form. One could as well write much more complicated costs involving some integral functions, etc. But once you understand what is happening here, other cases are adaptations. And so let us consider a function phi. And so here we minimize with respect to endpoint conditions here, where mu are solutions to this controlled continuity equation. So dynamic programming approach of optimal control theory associates to this problem so-called value function or cost to go function, which is defined almost the same way like in problem P. But only we change now initial time and initial state on the measures. So this V depends on T0 and mu0. While in our initial problem, T0 was 0 and mu0 is mu0. So you get a family of optimization problem instead of the one which you started. And what is nice about value functions that they solve some partial differential equation and allow to find optimal control. So to introduce now viscosity solutions, I need to introduce the notion of directional derivative of functions defined on metric spaces. So let us assume here W is defined on this product, and then take K, which will be a real number, and V will be some Lipschitz function. So directional derivative in the direction KV is defined by this maybe heavily looking expression, but if you spend some time looking on it, in fact, it is Dini or Lava-Dini directional derivative when W is Lipschitz function. And so here, basically, we perturb point T mu, which is here, in some direction, in the direction K, and the direction identity plus HV, push forward mu. And we allow here small also variations of this variable. So this is called directional derivative, and it is required that when we perturb, we should stay in the domain of W. If we cannot perturb in this way, then we simply say that directional derivative is plus infinity. Then Adamar subdifferential is defined using these directional derivatives. So we say that couple of scalar and L2 function is in Adamar subdifferential if this inequality is verified for every scalar K and every Lipschitz function V. And Adabar superdifferential is defined in this way. It is again inspired by finite dimensional context. And then one can show that in fact subdifferentials, like written here, are related to polars of tangents. So you see, you can transport now the geometry I introduced before using normals or even proximal normals to this subdifferential framework. So let us now go to Hamilton-Jacobi equations. So if we inspire by classical theory, it should be written in this way, where H is Hamiltonian. So Hamiltonian, since we are in the framework of Wasserstein spaces, is defined in the following way here. So we integrate with respect to measure, and P is a two function. And then here you see derivative with respect to time, but time is just in real time, so it is usual derivative. While here you see appearing gradient with respect to measure, but to define viscosity solutions, one does not need to know gradient, but rather sub and superdifferential. So the definition goes the following way. We consider sets delta R, which are couples of T nu. Nu is a measure here, such that the support of nu is contained in this ball. So it is something like support propagates according to propagations of solutions to continuity equations that I mentioned before. Then we say that W is viscosity solution to Hamilton-Jacobi equation if for every element in subdifferential this inequality is verified, so it is super solution, and for any element in superdifferential, opposite inequality is verified, so it is subsolution. And so if W is continuous, and for every R it verifies this kind of inequality, then we say that it is a solution on this product. So it is space of measures with compact support. So the first good news is that if we take phi continuous, then the value functions that I introduced before is solution to this Hamilton-Jacobi equation on this whole space, and it satisfies the final point condition. And uniqueness of viscosity solution, and this is the last transparency, is the result is as follows, that if we take a function W, which satisfies the endpoint condition, if the restriction of W to delta R is viscosity solution on delta R for any R, then actually this W coincides with the value function. So you can consider it as a uniqueness result. How this is proved? One introduces just epigraph, a dipograph of the solution W. One writes this extended system. So here is our controlled continuity equation. This is the time evolution, and this is function which is measuring property of solutions being monotone. And so one shows that if W solves the Hamilton-Jacobi equation, then W is non-decreasing along solutions of this system and is constant along at least one solution of such a system. And so to show it, one works on graphs, on epigraph of function W. That's why there are three variables. And so that's all I wanted to show you. To make conclusions, so non-local continuity equations that were formulated on Wasserstein spaces are used in various models to control evolution of probability of individual adjoints or sets of adjoints. And this Wasserstein framework is particularly rewarding when we work, because it allows to work with dual notions. So you have seen, I defined something which looked like subgradient, I defined proximal normals. And let me say that a lot of things we know from traditional classical control theory can be transported, in fact, to the Wasserstein spaces framework. One can, for instance, speak about semiconcavity of value function. One can show a result saying that value function is differentiable, something like Gateau differentiable along optimal solution. one can prove also Pontryagin maximum principle and sufficient optimality conditions in the sense of sensitivity relations. So I hope you could follow more or less everything, but I will be ready to send any reprints and also to give some more explanations. So thank you very much for your attention.
Thank you, Elena, for your kind talk. There are some questions in the chat already, so you can read it. So the first one is by Amatach on the measure.
Yeah. Okay. Okay, I don't see it.
Can you see, or I can read you?
Yeah, I don't see what I should touch here. So it is not in chat. It is in chat?
You are, yes, in chat.
Yeah, but when I open chat, so they should be on the top or down? Down, probably. No, I cannot go down, huh? So
okay, I can read you.
Yeah, okay.
Okay, so the first question is the measure mu as an expression, do we know its Borelians?
Borelian. Oh, you have to check that measures I define it on Borel sets only. So you, if you, for instance, you take a Borel set and you complete it like using Lebesgue measures, and you don't get a Borel set anymore. So in general, so these are measures for which the sigma field are only Borel sets, so nothing else.
So you have different expression of the function mu.
Yeah, that means that you have a mu, which is a function, in fact, a function taking values in interval 0, 1, and you associate measure to sets, to Borel sets. For instance, you can associate to a point x0, its measure will be a Dirac measure. That means that it's 1 at x0, and it is 0 everywhere else.
And in the slide of Meyer's optimal control problem,
yeah,
we can see explicit the measure mu, right?
Yeah, here we have a given initial condition, mu0, and then we consider this controlled continuity equation. We plug in controls, it's Lebesgue measurable function, and then under assumptions are imposed, Lipschitz continuity assumption, we know that there exists a unique solution to this equation. And then we consider cost associated to this solution. So it is phi of mu1, because it was chosen to only pay attention to finite condition. So if you change to another control, then you will get a different solution. So you are minimizing with respect to controls here.
Okay. And this is my question. For the compactness results, can we consider weaker assumption, or the list of the assumption is necessary, all these assumptions?
No, this is assumption that I put, it was just to unify everything in a shorter way, because basically you consider what is considered is Ascoli theorem, which will guarantee that the set of continuous functions will be compact if they take values in relatively compact sets for every time, and they are equicontinuous. And so these assumptions in particular guarantee these properties. But if you assume, for instance, that your set valued map take values in functions that are already equicontinuous, then you don't put Lipschitz continuity. So you can ask less, of course.
Okay. Okay, thanks. Are there other questions?
Let me just make one more remark, because I removed it from transparencies. To have this compactness, it was very important to have convex values. And where Lipschitz continuity is very important is so-called relaxation theorems. So if you take differential inclusion and you so-called relax it, take convex holes on the right-hand side instead of your original. For instance, maybe in your original inclusion, there were only 2 points, 2 functions for every t mu. But when you convexify, you make the whole interval of function between 2. And so what is happening here, there is so-called relaxation theorems that says that when there is Lipschitz continuity, then the solutions of original differential inclusion are dense in solutions of relaxed inclusion. So if you start by a problem where there's no convexity of right-hand side, but you have Lipschitz continuity, then you can say, oh, I can in a way simplify my model by putting convex holes, then I will have actually optimal solutions. A problem will be more easy to deal with. But then if your cost function is, for instance, continuous, then the value function will not change. It will be exactly the same because of this density property. And this is quite important. And relaxation theorems cannot be generalized by skipping Lipschitz continuity assumptions. So even in Euclidean frameworks, there are counterexamples. So, but for compactness itself, you can have much weaker assumptions. That's true.
Okay, thanks. So, are there questions in the auditorium? If
Okay, maybe I have more than a curiosity, right? Maybe for the people who wants to join this research area, if Professor Francesco can mention maybe some open problems.
Some of
open problems
let me say that there are quite a lot of open problems because in fact we started to do it something like 4 years ago. We're just 3 people and we're advancing. For instance, one could get interested by less regularity of the set valid maps. For instance, this viability theorem I have shown you, there were Lipschitz continuity everywhere, while original viability conditions set valid maps are just upper semi-continuous, but we don't even know if they are continuous if viability conditions are true. For invariance, one knows that one needs Lipschitz continuity, but for viability, one doesn't need. So this is open still. So now I formulated viability theorem here with P strictly larger than 1. When P is equal to 1, we manage to get viability theorem, but without using convex hull. And not having convex hull is quite bad usually in application because, you know, when you want to know if 2 convex sets intersect, you can think about something like separation theorems. When you have theorems which say that convex sets should be intersecting some non-convex sets, then one cannot apply a separation theorem to check it. So this is another question, what to do with P equal to 1? Can one get some similar results, which just I have shown you? And then there are also various results on parameterization, approximations, etc. If you look on book, a very old book of Cellino and Robin from the beginning of 80s, which is called Differential Inclusions. So this is quite complete theory in the case when set valued map do not depend on time. But then later on, there were a lot of papers were written also on time dependence. But in this book, there are many, many results. As for instance, you can take a set valued map which is upper semi-continuous, but you can, in its vicinity, always find the approximating Lipschitz functions. This is also quite useful result when you start to work with approximations and to try to simplify your problems. So these are also open problems. So then there's Lyapunov theory, for instance. I only spoke about Hamilton-Jacobi equation, but Lyapunov's second method can be also developed in this framework. We tried to do it just in the case when there are support of measures are compact, but one of course is interested in my general case. Yes, I think I can send you also this number of, but another possibility is just to look on what is known in classical differential equation theory and go ahead. Because most of things will be new in this context.
Okay, thank you very much. Thank you.
And Elaine, there is another question in the chat. I write for you. As it is mentioned in the first slide, should the measure mu be invariant by a measurable function?
No, wait a moment. Why you? I don't understand the question.
I don't know.
First slide. This was the slide. This one? No, not this one.
He wrote in the first slide, so
Which one? This one? I don't know.
probably.
No, measures are any
Yes.
probability measures which are Borel measurable, nothing else. So we don't ask them to have some invariance properties. So that just developed for general probability measures. I don't know if it answers the question. So
Yeah, I think yes.
okay.
Yes. This was the question, I think so. Okay, are there other questions? If not, thanks, Elaine, again. Thanks for your talk.
Okay, so thank you very much for attending.
Okay, and so now there is a break of 90 minutes, I think. So we will start at 1 p.m. for the Colombian time and at 8 p.m. for the European time for the last talk and the closing. So see you later. Bye.
Bye. Thank you.
Hola Diana,
Hola Brian,
se escucha bien.
muy bien. Vamos a esperar entonces a que podamos poner la presentación en este equipo y hacemos la prueba de compartir pantalla.
Eso, vamos a hacerlo igual que ayer. Entonces, ayer había otro computador aparte de ese
No,
ahí, ¿no?
este, directo desde aquí.
Ahí es.
Sí. Pues vamos a esperar unos minuticos y ya lo compartimos.
Me va a descargar el computador. Ya.
No puede descargarse.
Yo iba a ir a subir el computador, pero debimos haberlo hecho con más tiempo. Vamos a ver. Hola, hola. Vamos a dar un pequeño espacio para ultimar los detalles de la charla presencial del profesor Villaveses. Aquí un saludo para los que nos están acompañando. Nicole, que viene acompañando nuestras actividades desde hace años. Un saludo. eh, saludo a la profesora Rosibel y a todos nuestros participantes. Recuerden que después de esta última charla del profesor Andrés Villaveses, vamos a tener una ceremonia de clausura para finalizar el evento. Solo denme unos minutos más y ya terminamos de cuadrar.
La nacional, ¿cierto?
Sí, un día lluvioso. Es México. No sé.
Ok, buenas tardes. Vamos a iniciar con nuestra sección de la tarde. We're going to start with the last part of our event. And it's my pleasure to present you Professor Andrés Villaveses, who is a professor in the Department of Mathematics at the Universidad Nacional de Colombia in Bogotá. He's also a member of the Bogotá Logic Group. His main research interest is mathematical logic, doing research mainly in model theory, connections with geometry, set theory, and infinitary logic. It is a pleasure to have him participate in this event in person at the Javeriana Cali. And I'm going to say this in Spanish. Andrés Villaveses es un profesor del Departamento de Matemáticas de la Universidad Nacional de Colombia en Bogotá. También es un miembro del Bogotá Logic Group. Su principal interés de investigación es lógica matemática, investigando principalmente en teoría de modelos, conexiones con geometría, teoría de conjuntos y lógica infinita. Y bueno, es todo un gusto tenerlo en nuestro evento y agradecemos que haya aceptado venir a participar con su charla Pseudo Exponentials and Covers. Model Theory meets some arithmetic.
Okay. Muchísimas gracias, Diana. Thank you very much. Oh, the microphone here works. Okay, this is perfect. Okay. Muchísimas gracias. I'm going to give this lecture in English because there might be some people who join who are not Spanish speakers. But since we're all here in Cali and we, at some moments, I plan to give some kind of short summaries, like very, very short descriptions of what has been said in Spanish for, for our students here, for students, and for everybody here, or for anyone who wants to listen and also hear some kind of summary of some of the things that have been said at each moment. So two exponentials and colors, model theory meets some arithmetic geometry. This this reflects part of what I have been doing at Universidad Nacional de Colombia. You see in this, in the background of that image, on a rainy day, which we unfortunately do not have, anymore so many rainy days. We have now a drought in Bogota, but it's also a meeting point between what I have been doing for some decades, model theory, and some external parts of mathematics, well, algebraic geometry, and, as in the title, arithmetic geometry. So this will be some kind of a trip through several different parts of mathematics. Please feel free to ask any questions if you want, and I will try to clarify. This will be a little long trip, as we will see. Let's see. I'm trying to move this. Oh, I see. Okay. So in principle, we might be able to cover 6 stages. First of all, we're going to look at the exponential map and J in a very classical way, 19th century. We will start in the 19th century in the beginning. But, even before the beginning, I will give some kind of table of some of the directions that this has been taken. Then we will see a little bit some description of what model theory can do for us in terms of classifying theories. And I will also say and beyond, because we now no longer just classify theories, first order theories, but we also classify classes of structures that come from mathematical practice in many different ways. Then we go back to the beginning, but now with the language of model theory of the 21st century. So we jump from number 1 to number 3, from the 19th century to the 21st century. Then there will be a focus. This will be a kind of very short stage, just focus. If there is some kind of a take-home, like something that one would, dream that after listening to this lecture, there are 2 words that maybe I would be very happy if you remember them, if you don't know them already: categoricity and quasi-minimality. And then you can maybe reconstruct some of the things that we will be discussing from there. I will say some of what is happening. This is very recent work that we are doing, partially with one student of mine in Bogota, partially with some colleagues, collaborators in Chicago and in Oxford. And if time remains, because there was one student who asked me about what is Galois theory, model theory. This is tentative. I mean, if you don't have time, we won't go through this. But this also sort of ties up the whole thing. Anyway, so here we start. Very classical course, the exponential function and J. This will go to some interactions between model theory and arithmetic geometry. So we have classical function J that I will describe in a moment, from the half plane, the upper half plane, into complex numbers. And then here is a word of some theorem that is linked to the classification. If you don't know these things, of course, it doesn't matter, because here we would say a few things of how model theory interacts with those. And the names here, Am Harris and Boris Zilber. And the key word in model theory is categoricity. So in a way, this is in many ways a lecture about connections between categoricity in model theory and some different parts of mathematics. There is also the exponential function, or the pseudo-exponential function, that we will describe also in a moment. And then, again here, the name was Zilber. The mathematical word here is the Chanuel conjecture. And again here, it's categoricity for colors. So we will see some of those colors. Then there are some different things, some kind of more complicated things, Shimura curves, Euler curves. We don't know what they are. We won't see what they are here, but this is just for technical reasons. At the end, I will say a few things about something that is very new on mirror maps and uniformization. This is joint current work with Balvin, who is in Chicago, and Cruz, who is in Bogota. And we see word categoricity here kind of appears everywhere in different ways. So we will try to describe what it is in some way. Okay, let's jump back to very classical, late 19th century mathematics. Klein defines a function that he called J. It's the J invariant. The domain of the function is the upper half plane. So think of this as real numbers. This is the upper half plane. And it takes values in the complex numbers. So here Now, here's one definition. Of course, definition doesn't give much information, except maybe you see, well, if tau here is some element of the upper half plane, then if G2 and G3 are certain functions that I won't describe in detail, they are given by Eisenstein series, for instance. So you here have a quotient of analytic functions, and it exhibits some behavior that one might be interested in. Well, Klein and many other people were interested in this function. And this picture shows the values of the function. So each color corresponds to a value of the function. So you see already it's very fractal, and it's very, you see how it kind of regularizes as the imaginary part goes to infinity. But as you approach the real numbers, this really gets more and more and more complicated. This is like a foam, like an infinite foam spuma close to the real numbers. It has been described that way. And if you enlarge, if you zoom in, you get again the same kind of a complexity all the time. So of course, as you approach the real line, this will exhibit some very singular behavior. Now, as such, it could be an interesting object as such, given by some weird formula. But it turns out that this function is very important. This function is so-called an invariant, modular invariant of elliptic curves. And elliptic curves have been around for a long time. I mean, 200 years, roughly 2 centuries. Elliptic curves were originally invented in order to capture integration for ellipses. That's why they're called elliptic curves. But then there are objects that are really like tori, really. And well, it's an invariant of the tori. This will mean the following. If you compute, so let me, okay. If you compute, first of all, if you compute j at some tau, it will give you exactly the same value as j at this transformation here. So if you take a matrix in SN2 of z, A, B, C, D, and you apply this transformation, this will give the same answer. And moreover, what happens is if you take a torus, this element tau here parametrizes a torus, because the torus is really a quotient of the complex plane by the subgroup generated by 1 and tau. Remember, the tau is in the upper half plane. So when you mod out, when you quotient by that lattice, you get a torus. It's also called an elliptic curve. And you can ask, well, which properties of the elliptic curve are recognized by this value? And it turns out that 2 elliptic curves are equivalent as Riemann surfaces if and only if the values of the function are the same. And this is extremely dramatic because it gives you a classical 19th century style classification of elliptic curves or tori. So this is summarizing what I was just saying. So if there exists, so number one, there exists some element, some matrix like this in this particular group, such that if you act by this matrix, and where tau prime is here, it should be S of tau, really. It will be the image of tau by the action of that matrix. Well, if tau and tau prime are related by the action of such an element of that group, that's equivalent to saying that tau and tau prime parameterize, as I was just saying, this way, the same classical tori as far as Riemann surfaces go. So the 2 tori given by these quotients, C over lambda tau, where lambda tau, this subgroup I was just mentioning, 1 generated by 1 and tau, so it's a rank 2 subgroup of the complex numbers. These 2 objects are equivalent as Riemann surfaces if and only if the 2 objects are related by the action of the group. If and only if, remember the previous slide, if and only if the value of j is the same. So this weird map here that you have of j is a classification of all possible elliptic curves. So if you take like the green area here, all the green areas correspond to parameters of some elliptic curve, all the red one, but of course you have infinitely many colors here. Of course you have many colors. You have really continuing many colors here, and yeah, and counting many colors. And what's even more interesting is that there is this function that is holomorphic except here, of course, at the boundary, that somehow classifies all these elliptic curves. Okay, so that's, I believe, reason enough to pay attention to that object. Now, this object has been studied in connection to arithmetic geometry, to number theory, to a non-commutative geometry by changing the object in many ways. Understanding the behavior of J is an interesting problem, mathematically speaking. So far, logic and model theory did not really have access to such objects, such as this J, this function J. And what we will see is that somehow how in the 21st century, we started moving model theory and logic toward this sort of objects. It's not only this J. There are many other objects that are like this. The exponential function is another one. Maybe Riemann's zeta function will be another one. That's like a homework for the future for many of us. Because, well, the first part is giving you an object, a classical object, and telling you we should maybe pay attention to that object. I think this is compelling, reason. This is a very classical reason. But also, this is, doing this for J is emblematic because there are many other objects. I mentioned some of them before, Shimura curves, many other objects that are somehow a little bit like J in many ways. So maybe if you develop techniques that are good for J or for pseudo-exponentiation, you may also apply them, as we will see, to other kinds of functions. Now, what I have not yet told you is why, what can model theory do? Why on earth should you, look at logic? Why don't you just continue, doing arithmetic geometry the way it has been done for over 100 years, or topology or geometry, which are marvelous and fantastic? Why look at model theory? So I will do a short, very short, 30-second summary in Spanish of these things. Tenemos un objeto matemático muy interesante que viene del siglo XIX, un objeto clásico súper importante que ha sido analizado y estudiado de muchas maneras. Ha sido estudiado de muchas maneras distintas y tiene una tradición y es además emblemático de muchos otros objetos matemáticos para los cuales de pronto desarrollar técnicas análogas podría ser útil. La segunda cosa es que queremos acercar la teoría de modelos a este tipo de objetos y es, como decía, algo que eso sí es muy reciente. Y la parte que no he dicho todavía es ¿por qué? ¿Por qué vale la pena mirar esto con los ojos o con el lente modelo teórico? Okay, so we now continue. Oh, this was, okay, these are equivalent. And of course, this was also in the previous slide, but this is the justification for this function J. J of tau is equal to J of tau prime if and only if all of these things happen. Okay, so classical J is then an invariant of tori with several additional advantages. So it has an explicit formula, which I don't give you. It's a sum. It's really a series, and there are many people who can see a lot of properties in the series. It is a modular function that's kind of closer to number theory of SL2 of Z, and it is invariant under the action of that group. It captures isogeny. It is associated to the study of the endomorphism group for an elliptic curve. So all of these are side tracks that are extremely important and interesting. Each one of these lines could be, like a project to study some things. 1937, Schneider proved also that if tau is a quadratic irrationality, then J of tau, so if this is, like I, J of tau is algebraic of degree. And then you start seeing, well, there may be more connections than we expected from the initial description. There are many other things, like for instance, if e to 2 pi I tau, so this depends on tau. If this is algebraic, then the function at tau, the derivative of the function over pi, and the second derivative of the function over pi squared are actually mutually transcendental. So you see the relation here also gives some number theoretic information. And you might actually wonder, well, is there some differential equation that somehow governs the behavior of J? I didn't say this before, but yes, there is. And not only there is, but it has been studied, and it has been studied by my colleagues in mostly in Chicago, where they mix some model theory and that particular collection of differential equations called Schwarzian equations. I don't do that. I like it very much, but I take a different perspective. But this is just to, kind of to summarize why this is an important thing. There are even kind of recent important results by Pila and Zimmerman. They announced a proof of so-called Chanuel for the J map. I won't go into details right now about that. It is connected to Hilbert's 12th problem. Now, transcendental, okay, you don't see what is involved, but okay, this is transcendental analytic geometry. So this person who is here, the older looking one, this is in Bogota at Universidad Nacional, also this. This is Boris Zilber, who is professor at Oxford, who is originally from Russia, and or he grew up in Soviet Union, and he has been pushing this convergence or looking through the eyes of model theory, of some kind of model theory, at these sort of transcendental objects. So he started around 2001, a little bit before, to use axiotizations in the logic L omega 1 omega. Now, I won't describe in detail L omega 1 omega, but I tell you it's a logic where you can do infinite conjunction and infinite disjunction up to countable, because you need that in order to keep track of these functions. I didn't say this before, it's not in my lecture, but one of the problems of just taking the first order theory of the exponential map is that the exponential map is very nice. If you don't have the exponential map, model theory of the complex numbers is very well understood since Tarski, Seidenberg, there are many, really, it's what supports classical algebraic geometry. As soon as you add the exponential function, you take the kernel of the exponential function, then you have the integers. You can actually interpret the integers, which is okay, except all the Gödel phenomena, the Gödel theorem kind of creeps in and becomes very different from algebraic geometry, from arithmetic geometry. And that's why this L omega 1 omega, this kind of heavier control, better logical control of the structure is necessary. It's not sufficient to just take normal, finite disjunctions and conjunctions. You have to take infinite disjunctions and conjunctions. But he started this process. This was about like 10 years ago, and he has continued in many ways, pushing the boundaries through all other functions, as we will see a little bit later. So with Adam Harris, his former student, he extended this work to J invariants, and they linked categoricity, which I said I want to convince you it's important, to a positive answer to a Serre conjecture on Tate modules. So a very model theoretic notion, categoricity, that we will explain, is linked to a quite complex Serre conjecture on Tate modules linked to elliptic curves. I won't explain these, but I'm just telling you somehow this categoricity that we will see turns out to reflect itself through the use of this logic in important other mathematical products. So it's worth looking at it, I think. I have given you enough reasons for that. Okay. Now let's now, the first part, we arrive, or first, voy a 30 seconds in Spanish. Llegamos a un punto del camino un poco complicado con Serre y la categoricidad. O sea, vimos que el camino nos lleva ya L omega 1 omega y nos toca hacer un pequeño alto en el camino y bajar un poco, descansar un poco y aquí va a haber algo plano. Here there will be something flat for a while, and then of course it will start going up again. So now we start saying a little bit what model theory is. So you have this question that I think everybody here has asked themselves sometime, that question. Some mathematical structures seem less random, more canonical than others. Of course, it could be some kind of sociological question. You could say, well, maybe, for us, the real numbers are important, but maybe in some other planet, the real numbers are some weird field that nobody knows except some strange mathematicians. And for some strange reason, they all deal with some other field that only, very few people here, like some of the people who have been lecturing here, like Jesus, no, but Maybe it's, but maybe not. Maybe, you know, the integers, the reals, the complex numbers are really canonical for some reasons. So let's look a little bit at this question in a different way. So we can consider the formless magma of all possible mathematical structures. And you could say, maybe some people would say, well, it's some kind of random noise. We're just, you know, playing with random noise and there is nothing. But I say perhaps not quite. You know, groups, fields, algebraic varieties, so we have spaces, intervals of set theory, function spaces. Some of these have appeared here all these 4 days. And it's not a coincidence. Is it a homogeneous world? What kind of classification is there? Well, mole theory has a strong classification for all first-order theories. So remember when there was this L omega 1 omega that appeared before with Zilber, there was this, I told you, you can take count all infinite conjunctions and disjunctions. Here, we cannot take those. Here, we're at a kind of lower level, only finite conjunctions and disjunctions. And of course, existential quantifiers, universal quantifiers, and so on. These are examples of structures that are canonical. So these are just examples that everybody here recognizes. And some people say, well, I like these ones, and some people, no, I prefer these ones. Or of course, the list is longer, but there are some. And for many of these, we actually have very good tools in first order wall theory. And also words that appear attached to these things, such as dimension, rank, degree, density character, they seem to appear, you know, in many of these structures, and they control them and they allow us to capture them. Now, this is not a coincidence. This is not really a formless magma, as I was picturing before. This is not, mathematics is not random noise at all. And model theory actually gives you, first of all, you can look at arbitrary structures, which is very rich. But then among these arbitrary structures, it gives you a hierarchy of types of structures or the theories. That hierarchy is an enormous theory developed since the 1970s. It's called stability theory. Well, there are some other theories in mathematics that are called stability theory. This is model theoretic stability theory. In the best part of the hierarchy, there are some good things. Zariski topology, you can do some kind of simulation of Zariski topology, Zariski geometries due to Fushkovsky and Zilber, the same person in the photograph I put before. There are many other things. Let me jump to number 5. Recently, model theory has dealt with limit structures of various kinds, limiting processes of constructions. So mathematical approximation and perturbation theories, and that being also part of model theory. That is more recent. But let me go back to that question on the map. So the formless magma really has a little bit of structure here, not much yet you have some dividing lines. Some theories are this side of the red line, and some theories are this side of the red line, or the green line, or some other lines. The most important is stable versus order. Believe it or not, but every first order theory that you have either has a very good dimension theory and is kind of similar to vector spaces or algebraic geometry. It has very good dimension theory, or it has an infinite order. And each theory is on one of these two sides. If you have an infinite order, you cannot have such kind of a algebraicity. So the real numbers are here, of course. They are quite different. And that's why real algebraic geometry is quite different to complex algebraic geometry. The p-adics are here, but vector spaces are here, and many other structures are here. So having a dividing line like that for all theories is quite powerful. These are all kind of more technical dividing lines, DOP and DOP, or all top, no top. I won't discuss them. But you start seeing that among all possible theories, you have kind of these sort of dualities, dividing lines, that maybe now we can see in this map. So this big box is, all first order theories. And there are some areas, like that corner here has Cervelo-Frankel and so on. They are there, they're theories, and they are very different from algebraically closed fields. You do very different things. They are very interesting, but for different reasons. At this corner, you have something like algebraically closed fields of some characteristic. This is really this corner, the best understood corner of mathematics, I could say. Algebraic geometry is here. And then you start going, well, here you're a little bit farther away, and this is the so-called dependent area. There are many theories here. A word that you may see, all minimal, is around here. All minimal is very famous nowadays for applications, even in control theory and many things that have been mentioned here, and random graphs. Anyway, there are some other areas, but the map nowadays is nicer because there is a web page. It's an interactive web page run by Gabriel Conant, and it's very, very nice. It's the same map as before, but this is much more sophisticated. So we have the dividing lines, and you can click here on stable, and this is the stable part. The pink part will be so unstable will be here. But also it gives you, for stable, some examples from mathematics. And of course you can play with it. Just it's forhiddendividing.com. It's this word.com. So you can play with that, at some point. And anyway, you click on an area and it gives you what is common to all theories in this area, or in this area. You click on some of these important names because these are names that have been studied by many people. The person who started this was Aaron Shelah around 1970, but it's still being developed. I mean, the map has been filled for the past 50 years or so, and there are some areas that appear, and it's an extremely rich map, as you can see. And there are some important areas like stable, super stable, distal, NIP. Like NIP is very connected to machine learning, for instance, and omega stable is very, like this area, omega stable is where algebraic things that are similar to algebraic geometry. And here, O minimal is things that are similar to real algebraic geometry, and so on. So nowadays, model theory, first order model theory has this incredible map. By the way, this map is being updated as more theorems are proved. So probably if you open it now, you will see a more sophisticated picture than this one here, because this, I just, took the picture from maybe a year ago or something like that. And more theorems are proved and more examples are found. So this is kind of a very good summary of that development of model theory. I will jump over this because this is very interesting. This tells you that all theories are kind of organized in two kinds of functions when you count the number of models. But maybe let me just mention later spin-off from stability theory. So there was around 1990 Hrushevsky's proof of the Mordell line conjecture. So it was not the first proof because Faltings have given another proof, but this is a different proof. It's purely model theoretic. And it gives actually better bounds than the Faltings proof, which is amazing because model theory is logic. Normally, it was not really concerned with inequalities and bounds. It's not analysis like inequalities as we were discussing with the one yesterday, yet it gives very good inequalities. There is model theoretic analysis of some conjecture, arithmetic geometry, André Oort. There is very recently the proof by Casal, Freitag, and Nerlou, they published it in Annals Mathematics, of a conjecture by Perlevet from around 1890. I think this type, well, but it doesn't matter. So a conjecture from the 19th century was proved using these tools very recently. It's from 2018, using the model theory of differentially closed fields. Model theoretic analysis of analytic functions and Grothendieck standard conjectures, but this part not only in first order model theory. So you see, after a while, this, looking at this map has some interesting consequences. And as I was saying before, the original dividing line, the red one, from whose name the whole subject inherited its name, is the notion of stability. Okay, let me just push this a little bit more. Initially, model theory allows two basic things. First of all, capturing classes of models, and second, isolating definable sets within each class. Examples, classes of models are models of like Peano axioms for arithmetic, group axioms, field axioms, algebraically closed fields, etc. Hilbert spaces, if you add, if you enrich the logic in order to be able to speak about convergence, that has been done. That's kind of more new, but it can be done. And definable sets, there are two levels, and there will be a picture. Through a formula, definable sets, of course, because let me just look at this formula here. This is an elliptic curve, again, like in the beginning. But when you say, well, what is a solution set to this? You look for the x and y somewhere that satisfy this. Or you can take something simpler, maybe some parabola or some ellipse, and those are examples of definable sets. So for each definable set, there is, well, sometimes an equation, like here. Sometimes a little bit more than an equation. Sometimes it's a formula of logic. You can also, just as you find the solution set of an equation in classical mathematics ever since the Greeks, at least, each formula also gives rise to a definable set. So if you take a formula here, phi, a formula that you can write with for all there exist, blah, 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 you can always ask yourself, well, what is a set of all the pairs or triples of your model? Here it is the complex numbers, but of course you can change here to whatever you want and find those elements that satisfy the formula with these parameters, A, B, and C. And of course, you all know from your basic courses ever since high school, many examples of these things, like parabolas, straight lines, ellipses, and so on. They are examples of definable sets, but this is much more general. So classes of models and definable sets are the sort of things that we kind of have a very good hold of in model theory. Now, we push it a little bit more. We can take collections of formulas and have simultaneous solutions. As you know, a good part, an important step in mathematics is when you go from one equation to two equations. Now I have to solve two equations. It takes some effort the first time you do it in your life, maybe in school. Or sometimes, system of equations. System of equations then starts getting serious. You have to look at whatever, some linear algebra. Or if this system of differential equations, then of course you have to have some good existence theorems and perhaps some uniqueness theorems. And perhaps the notion of solution may be weakened, as we saw in Michael Rozhansky's lecture the other day. There are many variants of this. This is yet another variant. So here you have infinitely many formulas, and you have these solutions. So I have some examples here. The solution here is 2, the solution here is square root of 2, the solution here is pi, and here are some collections of formulas. The collection of formula is called the type. And you can see that there are realized types, the first one. Principal types, this is really generated by one formula. You just need to know one formula to describe the square root of 2. Or the more, perhaps most interesting, non-algebraic types, transcendental types. So your idea of algebraic number, transcendental number gets upgraded in model theory to algebraic element on the finitely many conjugates or solutions, common solutions, and non-algebraic or transcendental, if you want, types. All theories have these levels, and there are many ways of being transcendental. So turning things around, we also regard the set of formulas as some kind of very good definable set. I will jump over this because I like this picture. So here you have some base here, and you have A and B somehow share the same type. There are two different solutions. C is a different type. And this really starts looking like orbits of the action of the automorphism group of something, which is something that you can also do in model theory with some technical tools that are required. So I think this is a good moment for some summary. I think I'll jump over this. This is, maybe the last part. Types are really the basic blocks of information of generating, counting structures, and controlling embeddings between them. 30 seconds to understand. Tenemos entonces la lógica de primer orden, que tiene ese mapa impresionante contemporáneo que se ha ido armando y como llenando el mapa. Al principio era un mapa con muchas zonas vacías, ahora sigue habiendo zonas vacías muy interesantes y hay colegas realmente fantásticos en muchas partes del mundo, incluido en Bogotá, que trabajan en llenar ese mapa de muchas maneras. Es muy bonito y es poderoso, porque no es solamente llenar un mapa, sino es encontrar líneas divisorias que son realmente significativas. La más importante de todas, lado estable. Las cosas se parecen a geometría algebraica o a espacios vectoriales, hay nociones buenas de generado. La palabra técnica es rango de Morley, o sus generalizaciones, rangos modelo teóricos. El otro lado, el lado inestable, es porque hay un orden infinito. Y es un poco curioso, o hay orden o hay estabilidad. Y el mundo se parte en dos. Es curioso, ese es un gran teorema de Scheller del 70. Bueno, y ya los objetos son entonces estos tipos, los tipos son conjuntos de fórmulas que se pueden ver como sistemas de ecuaciones muy grandes. Entonces, un elemento de solución se comporta entonces un poco parecido a un trascendente o se comporta parecido a un algebraico. En el caso particular en que la teoría sea cuerpos algebraicamente cerrados, eso corresponde a lo que ustedes les han dicho que es algebraico y trascendente toda la vida, pero lo mismo puede pasar. También hay soluciones trascendentes de ecuaciones diferenciales y soluciones algebraicas en el sentido diferencial y en muchos sentidos, pero lo más impresionante es que esto funciona para muchas otras teorías. Okay, so we continue now, and these are some variants of types that I'd like to say. These are presented in 4 different ways. The first one was the one we said, sets of formulas, but it's also Zariski closed sets in some kind of topology. They're orbits under automorphisms, like in the picture, of monster models, strongly homogeneous and saturated. And more recently, they have been, there is some kind of probability space where these are measures and states or distributions. When a definition has these 4 or 5 equivalent formulations, you have in front of your eyes something that you have to pay attention to, because I described it this way, but you may have arrived through measures or distributions or automorphisms and group actions, as we were seeing yesterday in Jesus' lecture. Well, this classical relation between a theory and its models is very productive. It really goes on. There are many theorems. All of these theorems are like the first model theory course. One learns all of these properties. But now, let me give you another description of model theory from 1972, universal algebra plus logic. This was the definition in 72. In 93, it had changed. I'll just define it as algebraic geometry minus fields. So instead of an addition, it's now, well, it's like doing algebraic geometry, except we no longer have fields. It's a kind of a little joke of model theory. And much more recently, in 2009, Khrushchevsky described model theory as the geography of plain mathematics, which, I mean, each one of these definitions captures something. None of them really captures the whole richness of the subject. I will jump over these. These are classical theorems, but I want to get to some newer things. So these are all classical things. The most important is perhaps this, but I already said before. And I want to go to another map. So remember, we had that map. Let me go back, sorry. We had that map. This map is wonderful. This map is really interesting. But L omega 1 omega, like a J function and to exponentiation, it doesn't live in this map. It lives somewhere outside, somewhere, not really in this map. And in the 21st century, what my first contact with model theory was through a project by the same person who started this. So I don't share that. You'll see a picture of him in a moment. Although he did this picture and he still works in this first order picture that is so rich, he himself, around 1985, but very slowly in the 90s, and then it exploded in the 21st century, he himself kind of also gave a formulation, a very different formulation of what to do when you're outside this map. There's also life, because when you have a map like this, it's very nice for all the theories that live here. And you can actually say, and it's wonderful, and you can spend your whole life studying properties of this map. But there are many important theories, there are many parts of mathematics that don't live in this map in a natural way. Or, like exponentiation might live in this map, but it lives in the area where it should not. There might be, reasons to change this map. And this is what he started doing, what Schelach started doing around 85, 90. During the 90s, there were maybe 8 persons in the whole world who had looked at what happened outside of this. I had the honor of joining that group in 1997. And then in this century, it started really exploding in many interesting directions. So we will jump now to another version of this map that somehow reflects what has been happening now. The key word is abstract elementary classes. So I'll go to the map and then back to description of abstract elementary classes. This was the Conant map. And what we are doing is looking outside and maybe adding a further dimension to the map. And maybe, but this is a very, very bad picture, but maybe it's like surfaces that somehow occur over the map. This is just for, what is quite impressive is that in the 21st century, many of these lines of this map, many of the dividing lines have been expanded, sometimes in kind of twisted ways. It's not like a perfect projection from here. No, it really is more complex when you go up, but in a nice way. Stability, for instance, has a meaning outside. Now, what is that outside? So now we go back to a description we have here. So here the title is not visible, but it's algebraically minded model theory. Look, 1974, Shellac was already looking at those other logics. L omega 1 omega, I already told you, it's when you take infinite disjunctions and conjunctions. The model theory was, there were many things known, but it's much more difficult. It was much more difficult back then. L of Q is a quantifier. There exists uncountably many X such as that's something that is not capturable by first order logic. Anyway, he started saying, well, we can focus on the logic as we have been doing all the time. Let's change the focus. Let's look at how one structure is embedded into another structure, as they do in algebra. People in algebra start studying homomorphisms, morphisms. People in category theory, we saw yesterday also in his lecture, morphisms were there everywhere. And you built your groupoids and the algebroids and through morphisms. And this is essentially what Shellac says, well, yeah, logic is fine. I am a logician, he says, yet we will start kind of rethinking things as algebraists. So he kind of proposes this. The paper has a weird title, The Lazy Model Theoretician Guide. He put it as a guide for the lazy model theoretician. And we're still, since 1974, so 50 years ago, we're still kind of dealing with the consequences of some of the ideas that were put there. So that means that maybe the community is very lazy because half a century afterwards, we're still kind of opening up. It's one of those papers that are full of really amazing ideas. Amalgamation classes are some, but the key word is AECs. Abstract elementary classes are the ones that have consolidated in that map, maybe in the best way. So we have a seminar, it's called Conexión de Galois connection between UIC, University of Illinois in Chicago, and UNAL in Bogota. And that seminar has geometers and model theorists. So this guy, Anatoly Ligover, is somebody who was asking, okay, what is abstract elementary classes? He's Russian geometry, very good. He has been doing geometry of mathematical physics. And I like this description by Baldwin, my co-author in one of these things. For what's worth, AECs are a style of model theory that approaches mathematics in a more familiar fashion. Instead of syntax and semantic, so these formulas that we were seeing, one investigates classes of structures that satisfy certain properties, like closure and their limits. Indeed, there is a purely category theoretical definition that I won't give you. We saw a lot of category theory yesterday, not today. But here's a description. Abstract elementary classes are smoothly forward closed. That means that you take unions, you're still in the class, and there is a smooth way of doing that. Generative, there is a notion of generated model, and cumulative, coherent, this is more technical, model classes. Instead of taking axioms like you do the axioms of the group theory, groupoids, or you forget about the axioms, you just look at the class. If it satisfies these properties, it will have a rich model theory. And these properties, of course, you have to look at examples and look at what happens, but there are not that many. And the focus is no longer placed in which axiomatization you write, but rather on the sort of properties the embeddings between models have. What is amazing is that you can extract a logic from there. So it's what I was saying before, but in addition to the model class, there is a notion of strong embedding, which orders the class, refines on the right extension, closed under direct limits. This is what I was saying before. Again, endowed with an effective scheme of generated submodels, and with what I call a cumulative coherent behavior with respect to the existence of abstract solutions. Roughly, if you have some small model, you ask a question. If there is a solution somewhere, so if you have some enlargement of the model, and both of them can be enlarged to a third model that has a solution that somehow is coherent with both of them, then the coherence also happens between the first and the second. So it's a way of dealing with solutions in an abstract way. So now back to where we were. The map here is now like this. It includes many parts. It includes all of these examples of arithmetic geometry that I was describing in the beginning. They live really somewhere up here, and they live on top of the very good area, this little part here in the first order map. This area here is algebraic geometry and similar, and this is real algebraic geometry. Well, what we have been doing is extending these lines in the three-dimensional map. And what I want to focus in the rest of the talk, which is not much, that the upper part of that area. Okay. Now, the 21st century has seen then a lot of progress in structural dividing lines, superstability, categoricity. There are some names here of people who have been involved in the creation of that or extension of that map toward those areas. This is a picture of Saharon Shelah, the generator of these ideas of the first map and of the second map, although many people still work in the first map, and it is very rich, but I am part of moving to the second map. With him, we have actually we have been looking at the problem of extracting a logic for these maps. It's a very kind of going back to the beginnings, but in a kind of different way. So that's common work we have been doing with Shelah. So getting axiomatization of AECs in the logic. It was obtained in a form, but at a very high price, expanding the language through the presentation theorem. And we improved this recent result significantly. And now, with a student of mine in Bogota, Nicolas Nacher, we are kind of pushing the consequences of this new axiomatization and using it to get more canonical objects of many kinds. So this is kind of a story of the AECs. Okay, back to J and exponential scholars. Alan Harris, a student of Zilber, he provides a contrasting view of classical J invariants, that first map that we had here. He has an axiomatization in L omega 1 omega, and then a quite convoluted proof, his thesis. It's a proof of categoricity of this version of J. Let me say what the axiomatization is. So you take here field, you take here some map that will be like J, and here you take the group action. So remember there was this group action on H from the upper half plane. That's what you put in the language. So here F is an algebraically closed field of characteristic 0. I'm just saying what I said before. H is a set together with countably many unary function symbols, and J is a connection. So here's the color. You have H as a color of F, but you separate. You don't mix together. You don't look at H as a subset of the complex numbers here, but here on the left, you just have the group action, and on the right, you have the field structure. Now, this captures better the behavior of F, of J. Here, we have a lot of information. This is in the good corner of the map, in the best corner of the first order map. This is not. And then the connection is, well, it turns out to be, by his thesis, in a very good area. But in order to prove it, let me just say some of the elements that somehow are at play. So J here is a cover from the action structure into the field C. So here is part of the axiomatization. You take the first order theory, so all the things that you can say in first order. And here is an infinitary axiom that I think is interesting to watch. Let's read a little bit of that logic. For every x and y, if j of x, so I have to say here that these are in the domain. If j of x is equal to j of y, that means they are like tau and tau prime in the elliptic curve we had in the beginning, then for some element of the group, for some gamma I, x and y will be connected by the group action. This is somehow amarrando, tying up the group action. It's kind of saying, well, the group action won't kind of, when you look at fibers of J in H, you won't get non-standard elements in the fiber. So this is called standard fibers axiom. Standard fibers are exactly orbits. But you need this infinitary action, and that's why you cannot really work with this in first order logic. You're obliged to use this. If you don't have this, then you could have fibers that are not equivalent to orbits, and then things go haywire. I think se desorganiza todo. So this helps kind of tie everything. Let me go to, okay, his theorem is that theory plus saying that the transcendence degree of f is at least Aleph 0 is categorical in all infinite cardinalities, which means, and here's the definition of categoricity, that if you take two arbitrary structures, so now this J1 and this J2 are just some versions of J that satisfy the same axioms, but might have, quite different. This could be much larger than H, the classical H, or even smaller. It has to be infinite, of course, but this could be, any size. But let's suppose that they have the same cardinality, that this H here, F1, F2, have the same cardinalities. Categoricity means then that if you take here the first cover, so this M1 is here on the left, M2 here is on the right, then you have isomorphisms, one at the level of H and one at the level of F. So the field, this is here a field isomorphism. This is some, equivariant map. It really respects the group action. And this diagram commutes. The J function on this side and the J function on this side commute with these maps. And this is really an isomorphism of the color in this sense. His theorem, so that's Harris's theorem in his thesis, is that with that axiomatization, you can actually prove that for each cardinality, there is only one J. In particular, for cardinality continuum, for classical J, the axiomatization completely captures J. If you have in a logic a way of completely capturing a structure, then you are in a very good position because you have essentially found the perfect set of invariants for your problem. This is his theorem. I don't have time to go in the details of this. I can say this, that he uses a combination of model theory and arithmetic geometry. This is what he uses for model theory, quasi-minimal, but I won't go into detail of quasi-minimal. And he uses of arithmetic geometry, adelic Mumford-Tate, so things that you need to say quite a lot. But let me just say one thing. How you build an isomorphism when you have two levels, field level, and you also have at the top of the cover, the action. You have to understand how an elliptic curve, if these were elliptic curves, interacts with many families of elliptic curves. There are many classical theorems that tell you that if you build your isomorphism by a kind of induction of back and forth, but at each one of the stages, you have to say, oh, I already have these elliptic curves that I have been taking care of. I have a new one. How does it interact? Well, there is a lot of arithmetic that you have to kind of put into the proof in order to get to that categoricity. I will now go to the very last slide and conclude, because these are just additional classes that somehow this. The focus is maybe categoricity. There is a perfect collection of invariants. this is exactly what we were saying before. And I think I can close here for the model theory, of course. This. Thank you very much.
Muchas gracias, doctor Andrés. ¿El público tiene alguna pregunta para el doctor?
Sí, yo tengo dos. La primera es cuando se habla de estas estructuras que no son estables en orden, hay como niveles de esa inestabilidad.
Absolutamente, claro que sí.
¿Y hay un tope o
Sí.
es que me lo estoy imaginando como en las cardinalidades, ¿no?
Sí, pero fíjate, la primera parte, si hay un tope. Pero sí. No, voy a parafrasear la pregunta, entonces, simplemente, la pregunta es, primero, entre las estructuras, contesto en inglés o en español.
En español.
Ok, sí, entonces, si entre las no estables, las inestables, si hay una jerarquía, si hay unas que son como menos inestables que otras, ¿no? Y ahí la respuesta es sí, y la jerarquía, de hecho, sigue esas líneas, se puede decir un par de cosas más. La segunda parte sí tiene que ver con las cardinalidades, y ahí la respuesta es muy interesante, es ortogonal a las cardinalidades, sucede en cualquier cardinalidad. Un ejemplo de una muy inestable, teoría de conjuntos, es el ejemplo más inestable posible. Aritmética de Peano es como la siguiente más inestable y por eso es tan complicada la teoría de números clásica. Por eso la teoría de números tiene que valerse de la geometría algebraica, aritmética y todo eso para poder realmente resolver las cosas, porque si uno resuelve las cosas a la puro teoría de números, pues puede, y hay gente que puede llegar muy lejos, pero el avance en teoría de números se hace dando la vuelta por las zonas más estables. La jerarquía tiene unas zonas, una zona muy buena que no es estable, pero que tiene propiedades como muy cercanas, es la zona o minimal. O minimalidad aparece en muchas cosas, hay mucha gente que la estudia, incluso gente que no es de teoría de modelos, pero que le interesan ciertos problemas de análisis, porque son las expansiones de los reales. Las expansiones de los reales muchas veces, para muchas funciones, son o minimales. Ejemplo, la exponencial real, Wilkie demostró hace unos 30 años más o menos, fue un super teorema, que los reales con la exponencial real son o minimales. Eso muestra, bueno, no son estables porque está el orden, pero se pueden manejar, tienen, digamos, propiedades muy buenas que en cierto sentido explican o permiten hacer geometría algebraica real con exponencial. Ejemplo, cuerpos diferencialmente cerrados donde viven las ecuaciones diferenciales, esos sí son muy cercanos a estables, se comportan súper bien. Pero obviamente si no cambia el tipo de ecuaciones diferenciales, quién sabe.
Y mi otra pregunta era más una curiosidad de diseño, ¿no? Es que todas las gráficas tienen líneas curvas,
sí,
intersecciones, pero ¿por qué curvas? No rectas.
Bueno, ahí ya es la gráfica bien establecida. Al principio no había ninguna gráfica, pero luego el mapa se fue aclarando después de unas décadas y Gabriel Conant armó ese mapa interactivo que tiene las líneas. Y él de hecho también ha ido cambiando poco a poco el diseño, pero es un diseño plano. El problema ante el que estamos es, yo al principio pensaba, bueno, toca expandirlo hacia los lados, pero luego me di cuenta, no, porque todo está anclado sobre el primer orden, solo que es como un grado de complejidad mayor, es una dimensión mayor o varias dimensiones más. Entonces las dimensiones, digamos, hacia lo vertical, las líneas que aparecen ahí van subiendo, pero al subir se pueden ir medio abriendo en algunos casos. Puede pasar que una cosa que es una línea abajo, arriba se vaya como agrietando y abriendo, porque hay fenómenos que se ven arriba y no abajo. Y los planos estos curvos son como zonas específicas de las clases elementales abstractas que el omega 1 omega es el único que vimos aquí, pero hay muchos otros. De modo que esa es una pregunta más, digamos que ahí realmente lo que yo estaba haciendo no era matemáticas en sentido usual, sino tratando de pensar cómo sería el mapa, cómo sería, porque no existe el mapa. Es muy interesante que en todo caso muchos de esos puntos interactivos se suben, o sea, se proyectan como si fueran un fibrado, una especie de fibrado sobre esa especie de plano. Claro que sí, pero no hay ninguna formalización de eso.
Yo tengo una pregunta.
Adelante.
Justamente sobre tu comentario respecto de que todos son morfismos. Cuando se hacen semánticas categóricas, especialmente lógicas computacionales, por ejemplo, Ese ejercicio de tomar las fórmulas como objetos de una categoría, las pruebas como morfismos y las reglas como ciertas propiedades categóricas, permite extraer ciertas características importantes acerca de la utilidad computacional de esa lógica. Ese esquema metodológico, por decirlo así, se ha transportado a la teoría de modelos en ese estándar, digamos, tan elevado de morfismos, propiedades, objetos.
Ahí es muy interesante algo que está pasando, lo mencioné muy brevemente. Hay un grupo en República Checa, guiada por Rositzky, es el principal. Rositzky es un gran especialista en categorías, conocido desde hace mucho tiempo por conexiones con álgebra homológica, con topología algebraica. A él le interesaron las clases elementales abstractas porque él descubrió que son equivalentes a las categorías accesibles. Módulo, es decir, no es que sean directamente equivalentes, pero básicamente todo teorema que se pruebe para clases elementales abstractas se puede transformar en un teorema para muchas categorías accesibles. Allá uno podría devolverse y decir, ahora parto del punto de vista más morfismos puros, lo que estabas diciendo, y hago una pregunta. Eso todavía está en desarrollo, es de la última década esa conexión. Yo mismo no he trabajado tanto en esa línea, pero un colega mío en Bogotá, que fue estudiante mío, pero luego se fue hacia las categorías mucho más y trabaja con los checos, Pedro Zambrano, él sí conoce mejor esas líneas. Es súper interesante, pero ahí debo decir que no conozco tanto.
¿El público tiene alguna otra pregunta? Bueno, muchísimas gracias.
Bueno, agradecer al profesor Andrés Villaveses por aceptar nuestra invitación en ICMAM Latinoamérica y digamos las versiones preliminares de en lo que se convertiría ICMAM. El profesor Villaveses siempre estuvo presente, ¿no? Es por eso que nos llena pues de gusto que entre las 4 ICMAM Lectures que tuvimos durante el evento, pues el profesor Andrés Villaveses cerrara, digamos, con broche de oro, ¿no? Con su perspectiva amplia de las matemáticas, pues el evento, ¿verdad? Muy enriquecedor a las charlas presenciales que tuvimos con el profesor Jesús Alonso, con el profesor Michael Ruchansky y el profesor Carlos Koenig. Entonces, a continuación vamos a proceder con la ceremonia de clausura del evento ICMAM Latinoamérica, en el cual pues vamos a entregar el premio ICMAM, el ICMAM Prize, ¿sí? Por lo que entonces lo que continúa de la ceremonia, gran parte, se hará en inglés, ¿cierto? Entonces les pido por favor de pronto un minuto para compartir la presentación, ¿verdad? Y bueno, continuar con la ceremonia de clausura. Okay, so we are going to start the closing ceremony. Just to start, I would like to ask if Professor Carlos Koenig is there. Would you make him co-host?
Yes.
Professor Koenig,
Yeah.
Koenig, for being here. Professor Ewe Keller, are you there?
Yes.
Yes. Okay. Okay, so just let me start with the closing ceremony of ICMAM Latin America 2024. Right, this is a special opportunity, not just to join our mathematical community, but also because today we are going to know who will be the winner of the ICMAM prize. So the ICMAM prize, which was established in 2022, recognized outstanding Latin American mathematicians for their fundamental contributions in pure and applied mathematics and their efforts to enhance the international visibility of the Latin American mathematical community. Just let me say that candidates usually are nominated by the members of the ICMAM Latin America board, but also they can apply for this prize independently. Let me remind you that in 2022, the Colombian mathematician Tatiana Toro, who now is the vice president of the International Mathematical Union, was awarded this prize. So to start with the announcement of the ICMAM prize, just let me show you the plan of the ceremony. First, we are going to have some words by the president of the International Society for Analysis, His Applications and Computations, Professor Dr. Awe Keller. Later, I'm going to make some short presentation about the winner of the ICMAM prize. Right. Later, we are going to have some speech by the winner of the ICMAM prize. And at the end, we are going to know who will be the chair of ICMAM Latin America 2026, right? And then we are going to have our closing activity. So, Professor Awe Keller, the voice is yours now.
Thank you very much. Can you hear me?
Yes, we can hear you well.
Okay, thank you. Let me say, when the ICMAM community contacted us a couple of years ago, the ISAC community, to support them in their endeavor to establish all these things, we are rather happy to do that one, because they were a group of young Colombian mathematicians with a lot of energy who actually were willing to actually do a lot to actually increase the visibility of mathematics and mathematicians in Latin America in general, and especially Colombia in particular. But still, even while we are happy to do that one, we never actually expected it to be such a success, and we never expected the people behind that one to be that energetic and so on. And we are actually, looking back, I have to say, we are more than happy to have done that decision. And if I see this group of young Colombian mathematicians doing all that work, increasing the visibility, contacting, creating these conferences for everybody to participate, not only persons from Latin America, but also persons, I can also see persons from other countries, even African countries and so on, who in the past actually participated in that one. Then it's with great pleasure that we actually were having all these things. And I can only congratulate them for all these works they are doing. With all these extra works and so on, they also have to have their own scientific careers and their parts. So one can only say it was a wonderful work they've done until now. And we are more than sure that they will do it in the future. And we are more than happy to give them all the support we can give them from our side to this part, and also from ISAC, and bring them in contact and so on. And I can only ask everybody also in the audience, use the opportunity that you actually have here by getting into contact with persons inside and outside Latin America and so on. Use the opportunity to get your own visibility, to foster your own careers, and also foster the visibility of Latin American mathematics and Colombian mathematics in particular, which often is a little bit overlooked instead of being appreciated for what it is. So we had now a nice conference again this year, and I can only say after seeing all these talks and so on, that I'm more than happy to actually look forward to the next ICMAM Latin America conference. And I can only give my congratulations for all this work and to all the organizers. Thank you very much.
Okay, thank you very much to Professor Awe Keller for his kind words. So now I think all the people that are attending our conference also wants to know who is the winner of the ICMAM Prize, and it's my great pleasure to show you, to let you know that Carlos Kenny is the winner of the ICMAM Prize 2024. So please, I invite you to make a clap for this. Before hearing some words about Professor Carlos Koenig, to my understanding of his career, my modest understanding of his career, I will share some words about the mathematical career of Professor Koenig. Professor Carlos Koenig has been one of the most influential and prolific analysts in the last decades. The deep and broad range of his research accomplishment also includes many exceptional and seminal contributions. These are primarily in harmonic analysis and partial differential equations and the far-reaching connection between them. In his seminal work with David Jerison, he presented a new method to solve boundary value problems for elliptic operators with raw coefficients. His work with Robert Pfefferman, and Pfeffer on perturbation of second-order elliptic operators in the Lipschitz domain gave a new characterization of classical objects in measure theory. With David Jerison, Professor Koenig introduced the class of non-tangential accessible domains. This motivated the novel field of a study of boundary value problems in domains satisfying weak geometric conditions. In collaboration with Tatiana Toro and others, Professor Koenig has made groundbreaking contributions on the relation between the regularity of the harmonic measure and the geometry of the domain. In the field of dispersive equation, the work of Professor Carlos Koenig is very famous. In collaboration with Gustavo Ponce and Luis Vega, he was able to establish for the first time well-posedness for the Cauchy problem associated with the KdV equation, the Korte-Wick-de-Vries equation, and his generalized form with low regularity data via contraction principle. This work completely transformed the study of nonlinear dispersive equations. In fact, it's largely responsible for the extraordinary development of dispersive equations done by Koenig and collaborators and by a highly distinguished group of analysts. The global existence of solutions for critical problems is a central subject in nonlinear partial differential equations. In collaboration with Merle, Koenig designed a groundbreaking approach using a global geometric view of these problems by combining ideas of global geometry and variational methods. This work brings a completely new perspective into the field. In particular, in collaboration with Dukertz and Merle, Koenig has proved the soliton resolution conjecture for some non-integrable systems. In collaboration with Johannes S. Jostran and Gunther Ullmann, Koenig established an outstanding result on the Calderon inverse problems under partial measurements on the boundary. Koenig have received a wide range of awards, including the Salem Prize in 1984, the Bochner Memorial Prize in 2008, and the Solomon Leshes Medal in 2021. He has been an invited lecturer at the International Congress of Mathematicians in 1986 and 2002, as a plenary speaker at the International Congress of Mathematicians in 2010. He also served as chair of the program committee of the ICM in 2014. This task entailed designing the scientific program for the ICM has selected approximately 200 speakers for the Congress. Here Kenny showed his wide knowledge of mathematics globally and his ability to reach a consensus. Furthermore, he served as president of the International Mathematical Union from 2019 to 2022. During this term, the IMU faced two global and tragic events, namely the COVID-19 pandemic and the Russian invasion to Ukraine. Kenny's leadership and human skills were instrumental in guiding the International Mathematical Union from this difficult period. In particular, the rapid transformation of the ICM 2022 into a virtual event and the General Assembly relocation to Helsinki required the incredible hard work and dedication from Professor Kenny. As president of the International Mathematical Union, he also served as chair of the Fields Medal Committee for ICM 2022. He served as a vice president of the IMAS from 2015 to 2018. He is a fellow of the American Academy of Arts and Science and a member of the National Academy of Science in USA. He also is a foreign member of the Istituto Lombardo Accademia di Scienze and Lettere in Italy and of the Real Academia and la Academia Real de Ciencias in Spain. By all the metrics, contributions of Professor Kenny to mathematics are remarkable. Moreover, his collaborators, postdocs, and students can affirm even more. His global and visionary perspective and his unique intellect are accompanied with that extreme generosity to share ideas. By all the contributions of Professor Carlos Kenny to mathematics and his impact to the international mathematical community, it's our pleasure to announce him as the winner of the ICMAM Prize 2024. Thank you very much. Okay, so just maybe to Professor Kenny, we would like to invite you to maybe to share some words with the attendees.
Sure. Can you hear me?
Yes, we can hear you well.
Okay, very good. Well, I am very honored to receive the ICMAM Latin America 2024 prize. And I would like to give my heartfelt thanks to the scientific committee for having selected me for this award. I also would like to thank ICMAM Latin America for their organizing of many different mathematical activities in Latin America, like this very impressive conference, and also ISAC for fostering all this. This most determined support will greatly enhance the future of mathematics in Latin America. On this occasion, I would like to thank my teachers, Alberto Calderon, Anthony Zygmunt, Eli Stein, and Jean Fabes, for all they have taught me and for their invaluable support. I would also like to thank my collaborators, students, and postdocs for having greatly enriched my scientific life. And whatever recognition I receive is certainly also theirs. I first became interested in mathematics in high school when I was 12. I attended then the Colegio Nacional Buenos Aires, an excellent school in the humanities and the sciences. In my first year there, we had a class on the geometry of triangles, which was rigorous and with proofs. I discovered then that mathematical proofs mesh very well with my style of thinking, and from then on, I was hooked on math. Finally, I would like to thank my family for their love and support throughout the years. Thank you very much.
Okay, thank you very much, Professor Kenny, for being here, for accepting our prize, and for your support to ICMAM Latin America. Thank you. Okay, so also to finish our closing ceremony, just I would like to extend our gratitude on behalf of ICMAM Latin America to all the speakers, all the international speakers, the local ones also, for the amazing talks and for sharing with us for their knowledge and for talking about their research. Here we have the pictures of the speakers of the event. Especially also, I would like to take the time to congratulate and to thank all the organizers of this conference, especially to Brian Grajales, which is the executive director of ICMAM Latin America. Professor Diana Bueno from the Pontificia Universidad Javeriana. Karina Navarro, who is co-founder of ICMAM Latin America, Yuriko Pitones from Mexico, and Pedro Fernández Espinosa from Colombia. And also, we want to extend our deep gratitude to Jenny Fragnelli, our organizer from Italy, for all their hard work in this conference. We want to extend also our gratitude to Milton Aguirre for all the technical support given during the conference. So, as usual, when we are closing each Congress, each ICMAM Latin American Conference, we announce where will be the next event, right? So it's time to know in which place the next conference will be held, and also who will be the chair, the scientific chair of the conference. So it's my great pleasure to announce Pedro Fernández Espinosa from Caldas University as chair of ICMAM Latin America 2026. At this moment, I invite Pedro to say maybe some words about, in Spanish or in English, about this amazing opportunity that he gave us chairing our next conference.
Thank you, Duan. Just to end our meeting, I would like to say again, thank you everyone to be here during this week. For us, it was a pleasure organize this conference, and also on behalf of my university, Universidad de Caldas, I would like to express my deep gratitude to the scientific and the organizing committee to give us the chance to be the host in the next section of ICMAM Latin America in 2026. And we are waiting for you in the Open Door City, where everyone is welcome. So we hope to see you in 2026. En Spanish, todo el mundo está bienvenido a nuestra conferencia aquí en la ciudad de las puertas abiertas, donde todos ustedes son y serán siempre bienvenidos. Muchas gracias.
Okay, so then officially we close ICMAM Latin America 2024. Dejo el micrófono abierto.
Estuvo inspirado, pero realmente no. Simplemente agrego a lo que se ha dicho ya. Primero que todo, agradecimiento gigante a organizadoras de ICMAM 2024. Realmente es impresionante la energía, el alto nivel. Han puesto la vara muy alta para toda la gente joven. Ustedes son jóvenes también. Hay más jóvenes todavía, más jóvenes, pero realmente la energía que han traído, la novedad que han traído, el muy buen nivel, el premio también absolutamente fantástico a Carlos Koenig, toda nos pone un reto, y también nos pone un reto a quienes estamos ya en otras generaciones más arriba, digamos, más viejos también, porque de alguna manera el reto de, bueno, ¿cómo respondemos nosotros a eso que están ustedes trayendo en este momento? Todos, en todas las generaciones que estamos aquí, estamos ante un mundo que es difícil, es un mundo que está cambiando en algunos puntos muy preocupantes para todo el mundo, para toda la gente más joven seguramente y para todas las generaciones. La matemática juega un papel absolutamente central en ese cambio. Lo ha jugado por lo menos en los últimos 80 años, 100 años, desde que la matemática, con personajes como, pues, tan geniales, pero tan difíciles como von Neumann, por ejemplo, y muchos otros, muchos, ha traído dificultades. El mundo actual tiene retos creados por la matemática, pero la matemática también puede ayudarnos, no sé si a resolver todo, pero sí por lo menos a validar las cosas, a encontrar soluciones tal vez débiles, como nos enseña la matemática, a veces soluciones no clásicas, no absolutas, soluciones en sentidos débiles, sí nos permite, creo, ir encontrando a muchas situaciones. La matemática en ese sentido, y ICMAM es parte de eso, también es un instrumento de cierto tipo muy sofisticado de resistencia. Y utilizo la palabra resistencia, que es muy importante para nuestro mundo en este momento, no solamente en Cali. Y la matemática puede ser también un instrumento, un órgano no solamente para pensar mejor, para afinar nuestro pensamiento, para ver el mundo de maneras de pronto mejor calibradas, o por lo menos, como nos lo enseñaba, como nos enseña David Wigderson y nos decía en su charla, para aprender de nuestros errores. No solamente las máquinas pueden aprender de sus errores, sino nosotros también debemos, no solamente podemos, sino tenemos, creo, la responsabilidad, y es muy alta la responsabilidad para ustedes, jóvenes que están aquí, aprender de errores, muchos de esos no cometidos directamente por ustedes, sino tal vez por las generaciones anteriores, pero el hecho de que hayamos aterrizado en un mundo que es complicado, en parte por la matemática y en parte por otras razones, no quiere decir que no tengamos la responsabilidad de responder y de y de afilar nuestras herramientas, afilar nuestras herramientas. Es una metáfora. Aquí vimos muchas herramientas de la teoría de ecuaciones diferenciales, de soluciones parciales, de la lógica, de la geometría, del álgebra, de muchas otras partes de la matemática, de la computación, de la teoría del control. Afinar esas herramientas es nuestra responsabilidad para todos en este momento. Los mayores aquí, ustedes y los más jóvenes. Muchísimas gracias.
Bueno, yo aquí como para finalizar, si quería pues decir algunas cosas. Pues gracias a la Universidad Javeriana que nos abrió las puertas, tiene un campus muy bonitos con pavos y ardillas y de todo, tiene un campus maravilloso y gracias pues también a los profesores del departamento, profesor Carlos, gracias por ayudarnos, un saludo, no sé si lo esté viendo, pero si lo ve después al profesor Andrés Rivera, a la profesora pues, Diana, bueno, obviamente, que estuvo acompañándonos todo el evento, mejor dicho, y a los otros profesores que nos hayan acompañado en línea. Y también quería decir, pues, que digamos que uno de los objetivos que nosotros tenemos con hacer esto, o que tuvimos desde el principio con hacer esto, y lo comentábamos, pues, esta semana con los profesores Jesús Alonso y Andrés, que es más que todo para ustedes, muchachos que están como en pregrado, que están empezando la carrera, ¿no? Yo les agradezco mucho por venir, por tener la intención, pero digamos que, a ver, pues personalmente, por ejemplo, nosotros desde el pregrado ya hemos escuchado hablar del profesor Villaveses desde hace mucho tiempo porque el grupo de lógica de Bogotá es muy fuerte, es muy fuerte. Pues para mí es un honor y una oportunidad muy grande poder hablar con él, poder sentarme a conversar con él y ahí me iba a dar algunas ideas de matemática que sirven en investigación o bueno, tantas cosas que uno puede como que quedarse de estos eventos así. De pronto yo siento que puede ser un poquito desmotivante las charlas en inglés, sí, o de pronto los temas muy avanzados. No sé si ese sea su caso, pero lo digo porque ese era como mi caso cuando estaba en el pregrado, ¿no? Pero pues de todas formas yo creo que lo importante por ahorita, si tienen la oportunidad, pues es estar, ¿no? Yo, pues, lo que les decía, no tengo ninguna duda de que Duván, que es mi compañero de carrera desde el 2008 que entramos a la universidad, entramos juntos y nos graduamos casi juntos. Yo no tengo ninguna duda de que Duván es un investigador muy duro, va a tener una posición y va a necesitar alumnos de maestría, doctorado y hasta postdoc más adelante, yo estoy seguro de eso. Entonces, pues una oportunidad porque ustedes hablen con él si les interesa el área de él y quieren trabajar con él más adelante, tienen el potencial para hacerlo y sobre todo las ganas, pues aprovechen, ¿no? Aquí aprovechen, cojan el WhatsApp y hablen y bueno, la cosa. Sí, sí me hago entender. Entonces, pues chévere que hayan venido, esto pues lo hicimos para ustedes. Nuestros recursos fueron un poquito limitados, entonces pues nos disculpamos un poquito porque no pudimos ayudarlos más como quisiéramos. Nos hubiese gustado traer gente no solamente de Univalle, sino de otras ciudades para que vinieran y pagarles hotel y todo eso. Pero yo estoy seguro que si esto sigue creciendo y si seguimos trabajando como va, pues más adelante se va. Entonces pues gracias por estar aquí, un placer conocerlos y pues lástima que estuve como tras bambalinas todo el evento, pero aquí estoy ahora. Gracias.
Listo. Entonces, ¿alguien más quiere compartir algunas palabras? Sus avances.
Entonces, el reto sigue siendo de ustedes, los más jóvenes, para que sigan los ejemplos de los mentores y organizadores de este evento. Lo más importante de toda esta actividad es hacer comunidad matemática, para que sigan haciendo lo que más les gusta y les gusta. Muchas gracias.
Muchas gracias.